Hey, hello everyone, and welcome to FOSS XR 2022. So this year's, for second edition, we have joined with XDC and WineComp here in Minneapolis. And I'd like to really thank the amazing and wonderful team at Code Weavers for, mostly organizing everything for us. And so, big shout out to you guys. Thanks a lot for everything. It's really appreciated. So I'm Frederic Plourde, the XR lead at Collabra, and I'm really honored, and excited to be here hosting FOSS XR for 2 days to come. And if we think about, the first edition, I mean, we've come a long way. First edition in 2019 in Amsterdam, we had, I think, 9 talks in a single day. And today we're really pleased to be presenting to you guys 25 speakers over 2 days. And we're going to have also one panel discussion with a sister conference in Brussels happening at the same time. We're going to still also be presenting demo sessions throughout, scheduled throughout the 2 days, where you actually be able to, get your hands on really cool XR gear. And so I think it's a very ambitious second edition, but for a very ambitious mission, right? To get the traction and attention that free and open source XR software and hardware deserve. And speaking about being ambitious, so FOSS XR this year is fully hybrid, and so we're going to welcome 14 in-person presenters here in Minneapolis, as well as 14 virtual presenters, and of course going to be streaming all that live. So I'm super happy about this. I'd like also to thank our sponsors, the Kronos Group and Collabra, for without whom, of course, none of this would have been possible. And of course, so our sponsors are, are financing or supporting FOSS XR financially, and so they are supporting our mission. So I'd like to thank them. A big deal. A quick note to all of the in-person attendees. So we will be having the demo sessions that I just mentioned a minute ago. We'll be having those sessions in the Opus Hall, right? Just right in front of the XDC main conference rooms, in the open space. So, I would recommend at every break or in lunch breaks, let's all walk back to the XDC, conference area, so that we can have a chat with the people there and also, get our hands on those cool demos. And before we all start this, so one final note for presenters. Remember to to register on Matrix and log yourself in the FOSS XR chat room, because that is really the best way for us to contact you before your presentation, so that everything gets sorted out, all right? And so with all that being said, I wish everyone in here and people watching us a very good FOSS XR 2022. Thanks a lot. Hey Lubosz, welcome. So it's your life, so you can start. You are muted.
Oh, yeah, this was a hardware mute. Of course, I expected some technical issues. Let's hope this was the last one. So, good morning, Minneapolis, and hello to everyone else in the world. Welcome to my presentation about how to interact with your open source desktop in the far present. It's a bit verbal, so it didn't quite fit into the stream. But on this slide, I put the text size a little smaller. So it's actually my first presentation since the pandemic, and also my first virtual presentation. So I'm quite excited. I'm doing this from the comfort of my home. Let's hope the internet works. So I'm Lubosz from Collabora, and I've been working on XR for quite a while now. You know me from conferences like FOSS XR 2019, where I also did a talk about XR Desktop. So XR Desktop is the project I will be updating you on in this presentation. If you don't know it, it's a set of libraries and integrations into window managers that allow you to interact with your desktop in XR with integrations into KDE and GNOME. So when we initially released, we only had integrations into existing desktops with X11. But with this upcoming release, we have something new. So all of the work you see in this presentation was sponsored by Collabora, so thanks for that. We are doing really nice XR stuff at Collabora, so this is also part of that. Let me start with our stack, since it changed in the past, since the last release. So the last release was mainly doing a lot, reworking a lot of stuff, removing stuff that we don't need anymore, that grew organically, and resolving some technical debt we had. Since we started, a lot of the stack and open source VR stack changed. So we needed to adjust XR Desktop to that. So this is the old stack. I already showed this image sometime, maybe you know it. At the bottom we have our Vulkan wrapper. It's called Vulkan, and it's a G-Object-C library that does some convenience around Vulkan, since Vulkan is very verbose. And all of the above stuff is also using Vulkan, but at the very top with the window managers, we need to do some GL interop to actually share buffers. On the next level, we have GXR, which is the XR library. In this release, in the old stack, it had OpenVR and OpenXR support. OpenVR was also using OpenVR overlay, which is the equivalent to quad layers in OpenXR. So you just render on a 2D surface, and it was actually the first iteration we got, so render only on these quads. And later we also implemented, especially OpenXR needed that, I guess rather, at the time the Monado implementation needed us to render a full scene before it had quad layer support. But quad layer support was also not the way to go, so we always wanted to render a full scene. On top of that, we had the XR, or we have the XR desktop library that actually does the interface to the window managers and also implements basically everything that that has to do with interaction and everything above the low-level libraries. So we had the overlay app, which was only available on OpenVR, which rendered to these 2D quads, and we had the scene app that rendered actually a stereo full scene. And on the same layer, we have lib-input-synth. This is required to actually translate or to generate fake mouse and keyboard inputs. We have several backends in lib-input-synth, mainly for X11, I guess, XDO, for example. So with that, we generated button presses and keyboard input. And on the very top was the integration into the window managers, namely GNOME Shell and Kwin. In Kwin, we had the luck to only have a plugin, which made Kwin exchangeable, the Kwin version exchangeable, and only the plugin needed to be compiled against an API. On GNOME Shell, it's a bit trickier. We actually have a fork of GNOME Shell, so we are maintaining the patch on several versions. And it would be, of course, nice if we could change the situation at some point in the future. So this changed a bit. It's cleaner. I also aligned the boxes so it looks cleaner, but it also is nicer. So we still have Vulkan at the very bottom, nothing changed there. We still have GXR, but the new thing about GXR is that we only use OpenXR. On SteamVR and on Monado and whatever runtime you have in OpenXR. So we are very lucky to could simplify that. And then we introduced a new library, and that's the toolkit, that's G3K, where we do the object widget management and things like the cursor, containers, and I will talk about that a bit later. And on top, we still have the XR desktop library that interfaces with the window managers. A new window manager appeared in this, and that's WXRD, which is a WL Roots Wayland compositor, and it runs without another window manager, its own window manager. This means that we don't need lib-input-synth anymore, since we are the window manager. And we can basically synthesize input at the window manager level. So these are nice boxes, but let's show you some demos. Each of these libraries has minimal examples, so to get a feeling of what they can do at which layer of the stack, I will now show some examples. For example, this is a cube example. It's very similar to VK-Cube, the Intel VK-Cube, not the Lunar VK-Cube, but it does some shading, some phone shading. Yeah, so this example in Vulkan is 400 lines of Vulkan library code. So in Vulkan it would be way longer, and 98 of these lines are actually the vertex data for the cube. So it initializes a pipeline and does transformation with graphene. So nothing too fancy, so it's just a minimal thing that we can get on the screen, and it's using a 2D desktop window, since it's just a desktop example. So to show that Gulkan is not a toy library, I implemented a shader toy in it. And shader toy, I'm not sure if you know it, it's a collection of fragment shaders. It's a website actually done in WebGL, but it has an API, so all of this API access, downloading shaders and running arbitrary shader toy example is okay. I think I thought my desktop froze. Am I still there yet? Hopefully. Ryan is typing. I am still there. Thank you, Ryan, for giving me this comfort. Okay. Next example is an actual XR sample. So this is running on Monado with the XCB desktop window, and so the GXR minimal sample that initializes a multi-view swap chain, so with 2 array layers, and it's 450 lines of code, and it does like head tracking, and it's basically the cube in XR. We still need to like define the cube vertices and stuff. And the G3K is a level above that. So here we have a button, and it's 423 lines. Somehow the videos don't run that smoothly in LibreOffice. Okay, so much for that. The next release we are going to do is 0.16. It's been in the work for quite a while. So last release 0.15 is I guess already a long time ago. We also forked the master branch and did the work on a branch called Next, since we are changing stuff drastically. And there is no stable API in X.Org yet. Hopefully with 0.16 this will change. So basically, thanks to all contributors to contributing to this release. We have 70,000 insertions and 14,000 deletions. But I have to admit this metric is very confusing, since I did linter and code style stuff in this release. So basically every line changed. We see our G.SOC contributors there. We see Christoph. Christoph is, by the way, giving a talk tomorrow about X.OR Desktop as well, so don't miss that. And yeah, so it's a big release. As I said, we are the master branch. We are renaming that to Legacy for people that still want to use OpenVR overlays, and the next branch is becoming the main branch for 0.16. So what do we have in 0.16? We have the OpenXR overlay extension. So this is a screenshot by Christoph, who is showing 3 applications here. On the bottom is, I guess, the simple OpenGL example, or it's the Chronos OpenGL example, one of these. Then we have XR Gears, Vulkan sample I wrote for OpenXR, and it also has overlays support. And in the back, the thing with the birds, this is the XR Desktop shell example, it runs on top. So in Monado can actually composite these 3 apps. So it's really nice. XR Desktop can now run over other apps with OpenXR. Not that interesting, maybe. We are also using only the Vulkan Enable 2 extension now. It's available in Monado and ThemeVR. It just gives us more control to initialize our Vulkan stuff, and I guess it's the way to go in the future. And also, I also mentioned that briefly. We are using the VK extension Multiview. OpenXR also supports that by putting an array size of 2 in the swap chain. In GLSL, you also need to enable it, and you have a GLView index. This means you can a lot of stuff we needed to duplicate in Vulkan is now simplified for stereo rendering. So multiview is really nice, and multiview is the default way of rendering in GXR. So I guess every GXR sample uses multiview, and it's the way to go. We also last year we did a GSOC, and I also mentioned the GSOC students Remco and Manas in the commit log. So they did really nice stuff for X.Org Desktop, which is now finally landing in the 0.16 release. It's the virtual keyboard. So we now do have actually now it's in G3K. It's the virtual keyboard with support for 58 languages and emoji. So emoji is there in every language, and it has configurable layouts in the JSON configuration. So you could also do something non-standard or do bigger one or smaller keyboards as you wish. But yeah, we're shipping, I guess, these 58 configurations. And Manas implemented GLTF loading, which is really nice and also quite important for the future. And it's ported from G3. It's a GObject library that renders an OpenGL, and it has this really nice GLTF implementation, which we are based on now. It's certainly changed quite a bit. Also, so I already mentioned that, so WXRD, which was written by Christoph Haag, is our standalone Wayland compositor. With that, you can run XR Desktop on bare metal without X11 or any other Wayland compositor, which is pretty cool for embedded stuff. And yeah, we obviously have in WXRD, we have the power to render to DPI or fine granity sizes of windows that we don't have if we run in hybrid desktop mode. Since for hybrid desktop, it's always rendered for your display, and in VR we probably want a higher resolution than that. So it's nicer for text, basically. If you want to see more on WXRD, check the Collabora YouTube channel. We have 2 videos on that on there that show that. So one is with the Raspberry Pi 4, and one is on AMD SOC. So like and subscribe. So what I did recently is to improve the GLTF. So we now do have PBR material support with nice emissive roughness and metalness textures. We have in G3K dynamic pipelines that get dynamic attributes and compile dynamic shaders, depending on what the model needs and has. And we have a scene graph, thanks to Christoph, who started that. and we do nicer instancing in GLTF. So these are some models from the Kronos repo of GLTF that look nice. Like the fish, it's very specular. On the right, I think it's sci-fi helmet. It has an emissive texture, and in the middle is sponsor. That's usually used for testing global illumination, which, as you can see, is not present, but it loads. What is very important, we also now can render very nice controller models. So in this release, or in this version of X.Org Desktop, you still don't see a controller model. It's also like the WSD mode in Monado. And yeah, the link below, this is a collection of WebXR models we will probably ship at some point. Right, it's also GLTF. Now it's black. So the scene graph Christoph started, you can see in this with this model, it's a Lego Technic model which actually does a lot of distancing, and transformation looks fine. So scene graph works. Where to get this released? As soon as we release it, it's not released yet, so it will be, follow our Twitter, it will come in the next days, next week maybe. So we have Arch packages, we have, if you like, depth packages that are really recent, then check our CI, it builds depth packages, and you can also build it from source. Or if you're a packager, you can also package it, so we don't have to. Next thing is the G3K 3D UI toolkit. I already mentioned. So we have like common 3D UI elements in there. We already had since our initial release, but now they are a bit nicely sorted in the widget fashion with containers and scene graph. And for transformation, we use Graphene. It's a C library, but we did a lot of Graphene magic, and we actually need to upstream some of that. So we have a lot of linear algebra that makes stuff possible that we're doing. For example, we have containers that are head tracked. As you can see, it only is on one level. It doesn't rotate with the head, but actually it follows the field of view. So this is something like a model dialog in 2D. In 3D, it just follows you. We have a constant apparent size for the pointer. So what's that? So apparent size is something from astronomy. It's the size of a star in the night sky, even though it's bigger or smaller than you think it is. And we have this for our pointer. So on the left you see the pointer when the size is not, the apparent size is not constant. And this means if you hover it over an object in the front, it's bigger. So we don't want that. We want to be constant, and we still want to have its rotation. So the pointer is on the surface of the plane here, or of the quad, rotated with the surface. So we have that. So for the future, the G3K toolkit should, we plan to do like 2.5D UI. This is Firefox Reality, and as you can see, this is a UI as you would see it in 2D, but it's like on a curved surface, so you can put 2D surfaces with 2D widgets in 3D space. As it's known from all of XR apps. But we also wanted an old demo by Magic Leap, native 3D UI, which the demo of it is shown here. So for the future, what are our goals for the release after 0.16? So we want to have a full shell experience. So the desktop shell should be able to manage your device as a regular desktop with an app launcher and shutdown button and stuff like that. So it's not only a hybrid desktop mode, but also can control your whole device. We plan to use hand tracking over the OpenXR extensions available, as it's implemented by Monado, and we plan scripting for using geometry introspection. And of course, it would be nice to have a Flatpak distro, some kind of Flatpak distro for apps that use parts of our stack. Also, I have some nice 3D icons that will come together with this. These are made by Jakob Steiner. He's a designer for the GNOME project. He did many 3D icons for actually 2D UIs, but these are really nicely usable for 3D UIs as well. So we will make use of that. So left icon, for example, Nautilus or GNOME files, if you know that. And the one in the middle, I think, is photos. So the stuff is already there in open source projects. We can use that for 3D UI. And we also have already some mockups for the X.Org desktop shell. They are done by Tobias Platen. Check out his website. So basically, these are 2D mockups for 2.5D layouts that will then be in 3D, as you can see in the sketches on the right. So this is already in the works, but it won't be part of this release. Right, and you can do apps with any arbitrary part of our stack, like I did. For example, like in 2016, let me tell you a longer story. In 2016, I made GSD plugins VR. It was a VR video player, and was totally done in the GSD pipeline. And I also rendered a sphere mesh, and it could only do equirectangular 360 and mono video. So basically the interesting part was VR Compositor, which rendered the scene, got its transformation from back then OpenHMD, and also did even the thing that the Monado Compositor does these days. So it was basically everything in this pipeline. But these days, I thought this is not the right approach. So I did Sphere, the Sphere from 2022, because back then I also called something Sphere, very confusing. You see the GitLab link down below. So Sphere is using Golkan and GXR to render into VR, and it's using GStreamer AppSync, which is, I think, the right approach. So doing the VR out of GStreamer and just decoding the video in AppSync. I'm actually using Vulkan to get, so I'm constructing a Vulkan pipeline to get the VK image from the AppSync. And the sphere is in raycasted in the fragment shader. And for cube mapping, I do cube mesh, since I now do multiple projections. So sphere does mono stereo, 180, 360, and it does equirectangular cube map and EAC. So these three projections, both in stereo mono. Yeah, check it out. So for X.Org desktop, This was just an example for an app that is using the stack, and it should. I actually wanted to use G3K in Sphere as a demo, so to use it in other apps to open a file and stuff like that to have 3D UI work in progress. If you want to get involved, join us on Matrix, follow us on Twitter, like and subscribe, clone our repos, and now next thing is, or last thing, I still have 5 minutes on my clock. That's perfect because I want to do a demo. So demo, I thought, which device can I do a demo on? We already did, or Christoph will do one, I guess, on the Raspberry Pi. And so I didn't use that. Last time or last on the video I linked, I showed, I did it on this AMD SoC. It's a really nice box. So I already did that. I looked for devices where can I do this demo on. So I found this thing, but I think it won't run on XR desktop. So I chose this thing. It's my Steam Deck. Yeah. So disclaimer: this demo is not associated with Valve in any way. So this is my private Steam Deck. I needed to wait for it for several months in line, and it's actually it has the stock image installed. It's luckily based on Arch Linux, so I was feeling at home. And it's actually, it could play Stardew Valley right now after I reviewed it, but it's a vanilla Steam Deck. Yeah, let's try this. So I will change the camera now. So the camera is now this, nice. And let me disable the screen. So can you see this thing, this stuff? Hopefully you can. Okay, cool. So connected is, this is just an off-the-shelf USB hub. It has a keyboard connected. It has the HTC Vive connected. So this is an HTC Vive. I actually tried it with the Index, but was not lucky to make it work. So HTC Vive it is. The Vive is connected over DisplayPort. I actually was not able to make any HDMI work besides desktop monitors. And here is the power supply. So it's basically just a keyboard. So for this thing to be battery only, the Vive would need to be powered over USB, which is not possible with the Vive. So let's try this. Yeah, it comes up from standby. So the deck is in TTY, as we all know it. Let me fire up the Vive. It's on. Okay, so what do we do? On the first TTY, we run Monado. Seems to work. Yes, it does. So Monado does show up on the Vive. On the next TTY, we fire up WXRD. So this is done, I built everything in a CH root. That's why all the commands are quite long. So now we already see WXRD fired up. And on the last TTY, yes, we run gedit. And here it is, gedit. Let me do this. Right. Yeah, gedit on the Steam Deck with the Vive. So that was the demo. Can change my camera back now. Okay. And let me.
It's spread back here. You can hear me?
Right. So, are there any questions? Thanks. Okay, apparently you heard everything. Okay, that's good. So you can, I have chat open, you can ask questions from the chat.
Can you hear me, Lubosz? Hey, Lubosz, you can hear me?
Right. So there's a question about hand tracking input gesture. If I have...
Can you hear us, Lubosz?
Right. Yes, I can now.
All right. We'll have time, I fear, just for one quick question, and then we'll pass the mic to the next presenter. Make sense?
Right.
Do we have someone in the audience here?
So there are at least 3 questions in chat I could answer. Yeah, let me start with answering quickly the chat questions. Hand tracking gestures. So now I think we will start with something simple that's known and standardized, but there are not specific plans for certain gestures yet. But right, gesture detection would need to be a part. Hopefully, it can be done with an external library, so we don't need to do that as well. But yeah, I didn't figure it out yet. So first steps are actually getting the hand and the model of the hands, not only in rendering, but also in input. What's the scope of 3D UI? Right. So basically, first step will be what I showed in the Firefox reality demo. So 2.5 DUIs is, I guess, a good first step. Also for apps like Sphere. I could hear Fred, but I can't anymore.
So that's, I think that's it, Lubosz. Thanks. Thank you very much for this presentation.
2 questions.
And you
So I
can
guess
hear
I'm
me.
out of time.
Yep. So
thank you for listening. Follow me on Twitter if you have more questions, or ping me on Matrix. Okay, so have a nice conference and looking forward to the other talks. Yeah.
can you see that okay?
We can see you, thanks, and you're good to go.
Awesome.
Let me just move to the presentation.
Cool. Yeah, so hi everyone. I'm Adam. This is Rodolphe. Yeah, we're going to be talking about hand tracking. Sorry, we're just getting a bit of an echo. We might just need to mute.
I can mute our monitor.
Yeah. Yeah, we're going to talk about hand tracking and some open source tooling you can use to use hand tracking in your XR applications. Thank you. So yeah, I'm Adam. This is a picture of me when I had a bit more hair. So I've been working in XR since 2016, and I'm now the XR engineering lead here at Ultraleap. My first headset was a Google Cardboard, and amazingly, I'm still working in the industry despite all those roller coaster demos, making me feel very sexy.
Hello everyone, I'm Rodolphe Houdas. I'm working at Ultraleap as a field application engineer, which means that I'm basically helping customers in the integration with our hand tracking. I'm also what we call a FOSS evangelist, which means that I'm very increasingly annoying with open source software in the office. I also had my first headset was also a cardboard, but even worse, it was a knockoff of a cardboard. So yeah, I'm joining Adam on his opinion on it.
Cool. So yeah, we both work at Ultraleap, which is a company that formed from Ultra Haptics and Leap Motion merging. So we do mid-air haptics and hand tracking, but today we're going to focus on the hand tracking and specifically in XR. Leap Motion has been doing hand tracking since 2010, and in 2018 open sourced the Northstar headset, which you may have heard of. There's actually a couple of talks coming up on Northstar, which I recommend you go and watch if you want to learn more about it. It's an open source augmented reality headset. I know Bryan is giving a talk this afternoon. I think there's another one. No, Bryan's in a couple of hours. There's another one this afternoon. Anyway, we're talking about hand tracking, but what is hand tracking? Well, I like using this GIF to explain it. So what we can see here is that your hands are being represented in virtual reality in this case. So we have the ability to know where those hands are and what they're doing, what pose you're in, and tracking all the joints there. This then allows us to visualize them in XR. So as we can see, these captured hands here doing the same motions that the real hands are doing. It also lets you interact with virtual objects, such as this turntable. So that's really what hand tracking is. We can take your real hands and bring them into XR. So in this talk, we are going to look at tracking software. So how you can actually get hand tracking available in your headsets and systems. We're going to talk about OpenXR and what that means for developing apps with hand tracking. Then we'll look at the engine plugins and how you can kind of get data into your engine of choice. And finally, just plug some other little open source projects that Ultraleap have done along the way. Rodolphe, do you want to talk us through the tracking software?
Yeah, so we're going to start with our tracking software itself. It's going to be in two parts, basically how it works and on what. As you can see, there's already a flurry of logo. The headset that you can see with a weird cable on it is a Pico Neo 3 Pro on which we have added our camera. So we are also selling a bundle for it. First, I think it's important that we point out how it works, because there has been a lot of rumors on how our system works. People have been saying that we are using LiDAR, other people have been saying that we're using ultrasound, because as Adam said, we also have business in ultrasound mid-haptic, which we won't talk about it today. So first, it starts with really just simple cameras. I said simple cameras, but they actually have a twist. So the first one that you see on the top is the SIR 170. It's our latest product. and the one in the bottom is the Lib motion controller, which has been on the market since 2012. I'm also going to point out that the latest version of our software works with the Lib motion controller. So if you have one Lib motion controller that you have forgotten in a drawer, take it out of the drawer, download our software, and try it again, because right now it's way better than it used to be. One thing specific with our cameras is that they have 2 lenses, and they also have small IR LEDs. And those IR LEDs, the frequency that they are emitting is synchronized with the frame rate of our cameras. This way we can illuminate the end while also lowering the energy usage, which is very important for mobile platforms like VR headsets. So what you do with this camera is you basically install it on your headset, and then you plug it into your computer, and you use our software that will pull the images out of those cameras. And all those images are infrared and will be shown as grayscale. As you can see, this is a real-life example of what our camera sees, thanks to the illumination and the very short timing for the camera. We can basically remove the background as it will appear dark while the hands are still illuminated. So what we do with those images is that we fed them through a neural network, which is what you see here represented on the screen. That's how we represent a neural network, obviously. And this neural network will basically output skeletal hand data, which is 26, 27 joints, but Adam will talk more about the joints later. And this data can be consumed by an application client, or as you'll see, a plugin for game engine. So what it looks in practice is what you see right there. It's what you can see in our Unity plugin. So the data is pulled from the service, and then we are going to deform a mesh around them to look like your hands. In this case, because it's October, I decided to use a skeleton hands. If you're interested more about hand tracking, which is a very interesting subject, and you want to see how it can be done differently and on a different platform, go see Moses Turner talk this afternoon. I don't know what it is about exactly, but I'm pretty sure it's going to be brilliant. Let's see what platform is supported. So I want to point out first that the tracking software and the hardware is our core business. So we're selling the cameras, and we're selling the tracking software with a license. And for those reasons, they are not open source. Basically, all our tooling is open source. Only the core is not. If you use our hardware, you have to use our tooling, which is not exactly true, but we'll see more about it later. So the first release, I want to say the first release of a new generation of tracking was made on Windows, which made a lot of people very angry, because for years people have been asking for Linux support. And we have good news for you today, is that there is no on Linux. I want to point out that it's a beta, and it doesn't work yet with the Lib motion controller. But on our website, you can find instruction, those exact instructions on how to add a repository to your so it's only Debian based, obviously, a repository to your package manager, and then by using apt search ultralib, you can find what package we distribute. So there is one that is a meta package. I don't need to care about it specifically, but what you'll find in it is one service, which is a core service itself, one control panel that helps you debugging and showing your hands and making sure that your camera works, and most importantly, an OpenXR layer that works with Monado, but we'll talk about OpenXR later in the talk. And there's only one caveat with our latest generation of hand tracking so far, is that it only works with machine and CPU that have support for AVX instructions. There's no official support on ARM yet, but we're always interested to know if someone get it working with Box 86. Although without AVX support, it might be a little bit tricky. And finally, we also have Android support. Unfortunately, this is not publicly available, but if you are creating your handset that is based on the XR2 Qualcomm chip from Qualcomm, sorry, and you're interested in adding our hand tracking, please contact us. As I said before, this works with OpenXR, but you might be wondering, or maybe not, because it's FOSS. What is OpenXR? And Adam is going to present it for you.
Thanks. So Yeah, OpenXR. Obviously, with Kronos sponsoring the event, I imagine we'll be hearing a fair bit about it over the next couple of days. So I'm not going to tell you what OpenXR itself is or kind of any of the details there, but I'm going to focus instead on the hand tracking part of it. If you want to know more about OpenXR itself, I'm sure there's some great talks coming up. I know that Bryan is giving a talk tomorrow about OpenXR on Android specifically, so check that out. But in terms of hand tracking, Ultraleap joined the OpenXR working group in 2019 to help with the hand tracking extension that was being developed at the time. This extension has now been published and is available and supported by quite a lot of vendors. It's a multi-vendor extension and is supported by Microsoft and Meta and so on, and obviously also by us. So this extension is essentially an open API for getting hand tracking data. So you don't have to use our proprietary API or someone else's in order to get that data into your application. What does that look like in practice? Well, as Rodolphe mentioned, we're tracking 26 joints across the hand, and they're the ones in this diagram. So 26 joints per hand. And the API allows you to get the position and orientation of each of these joints in a vendor agnostic way. What this means is that you can get this hand tracking data into your application and use it via the same API, regardless of who the underlying provider is. Now, it's probably pretty obvious how that would work if you're using a headset that has hand tracking built in, such as the Meta Quest or the Microsoft HoloLens. But what if you're using desktop VR? Well, that's where our OpenXR API layer comes in. So in this diagram, I've put pieces of software or hardware in green and then API in purple. So despite being called an API layer, it is actually a piece of software. And generally speaking, what an API layer does is intercept calls from an application to the runtime that are being made via the OpenXR API. So what this allows the API layer to do is either pass through the call to the runtime if it doesn't know how to respond to it itself, or intercept that call and respond directly to the application, but in a transparent way because it's all being done by OpenXR. So what this means we can do is we can intercept calls to the hand tracking API and return hand tracking data to the application in a transparent way. So the application doesn't know any better that it's not getting it directly from the runtime itself. This means you can add hand tracking support to runtimes that don't directly support it, such as SteamVR. And on Linux, Monado, they do obviously also support their own hand tracking. So this means you can build applications using the OpenXR hand tracking API that work across all hand tracking providers and headsets, which is obviously really cool. Our API layer is supported on Linux and Windows and Android. And on Windows and Linux, it comes with a normal way of installing it. It's in the installer that you download for Windows, and it's via the Debian package that Rodolphe was talking about on Linux. I want to give a shout out here to StereoKit, which we used heavily when building our API layer because at the time no one else supported it. Supported hand tracking via OpenXR. And if you want to know more about StereoKit, which is a code-first library for building XR applications, Nick is giving a talk on that tomorrow. So I mentioned that the hand tracking extension is a multi-vendor or vendor-agnostic extension. You can also build vendor-specific extensions in OpenXR if you support functionality that other vendors don't get. And Ultraleap has published one of those so far, which is an extension for adding the 27th joint that we track, which is the elbow. So if I play this video, you can see what that means. So we're tracking the hands, but with the addition of the elbow, we can also show the forearm and use that in the tracking. Now, in this video, one of our developers, Matt, has been a bit clever and also inferred the positions of the shoulders and added the upper arms as well. But even if you don't do that, just being able to get the forearm into the application is really helpful for immersion. So that's available already via our API layer, and it's the XR Ultra hand tracking forearm extension. So with OpenXR, we can get this hand tracking data up out of a runtime or an API layer in a vendor agnostic way. It's all very well and good getting this data, these joints, but you actually have to do something with the application layer. And that's where game engine plugins come in. So over to you, Rob.
Thank you very much. So, game engine plugin, find the right plugin for your game engine of your choice. This will be a short overview of our plugins for game engines. We'll start obviously with, we'll start with an engine, but Adam and I are mostly Unity devs, so it's going to be maybe a little bit too short because we are not aware of all the features it includes, but I can tell you it includes a lot of features. So let's start. So Unreal Engine has always been supported throughout the life of our tracking software, but it has always been a little bit behind compared to Unity. We are targeting right now full feature parity with Unity, which is why we're hiring new people for that. It has been available on the Unreal Marketplace for a few years or directly from GitHub. And right now it supports Unreal 4.27 and above, which means also version 5. So what it includes is a core set of features that you'll find in any of our plugins with things related to hand tracking. So basically displaying your hand and responding to events like a pinch or grab. Another thing that it has, is an interaction engine, which allows you to interact with virtual objects by either pushing them or even grabbing them. You can also balance things on your hand if you want, and if you're really good at this, you might be able to juggle. So yeah, I was never able to do that. In real life, I know how to juggle. It also has a UI input module. So in your game or application, you might want to display something like a menu, a pause menu, or is an inventory of your character. And usually you use UI inputs for that. Unfortunately, it might be a little bit hard to work with hands. So what we did is basically a system that you can drop into your project and it will make your hand work as a controller on any UI input system. And finally, it also has a set of hands. So those are all the hands that are already given to you in our Unity plugin, in our Unreal plugin, and Unity plugin as well, actually. And they are also open source, so you can use them in your application. You can also modify them and redistribute them, obviously. And we also have a lot of other stuff in this module for hands. We also have a system that allows you to auto-read your hands on the end data, which means that you can also, if you're, for example, playing with an avatar or with MetaHuman, you can actually read your avatar or MetaHuman hands to your real hands. Now we're going to have a look at Unity. So Unity, as I was saying before, it has been the most developed of our plugins. And right now it is available in OpenUPM as a Unity package directly from our GitHub directory. As you can see here, it's showing how you can add a sculpture registries into your project and it will automatically import all the package for you. It also solves all the dependencies correctly. It's a great tool that we have that now. It's divided right now into two different packages. There's one called tracking and one called plugin preview, so I'll go over both of them. So first we'll have a look at the tracking one. The tracking one basically contains the same set of core features that you might find in Unreal Engine or other any plugin or scripts or binding, which is basically reacting to hands event and showing your hands. But as you can see here, for example, we have a system where with a pinch you can draw in space, so that's our painting demo. And we also deliver with it interaction engine, which, as in Unreal, allows you to push or select objects, but also to pinch to move them, or even to scale them, or if you go crazy, you can even rotate them. One thing that is interesting to note is that all of that works with OpenXR, which means that you just have to drop a prefab for OpenXR in your scene, and everything that you have done that is working with our plugin will work with OpenXR, which means also that if you have another hand tracking that works on your machine, you can use our tooling and plugins. You can use this interaction engine to interact with your virtual object directly with your favorite hand tracking system. So I like to say that our tooling might be built for hand tracking first, but it is not limited to it. Now we'll see a little bit of tracking preview, because I think that's what holds the most exciting things that are planned to be included in the core. The first thing is XLR interact, 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 XLR. Now, so we are looking at this system, which is pretty simple. All it allows you to do basically is to grab an action on a virtual object, and we thought, why not use our hands as a generic controller, because we already have two buttons, which are the pinch and the grab. So we did that, and they turned out to be very useful, very easy to do. Now with our preview package, you can, so if you import our preview package, you can just drop the prefab into your scene, and it will work out of the box 99% guaranteed. I never go to 100%. So yeah, another interesting features that we have is physics sense. I think that's something that has been talked a lot about online. You can see an example here. So basically, physics sense might become one of our best features and actually replace our interaction engine. So watch out for it. If there's something called interaction engine 2, that's probably it. So what it does is basically it uses the Unity physics engine and all the new articulation body that has been integrated since Unity 2020. And it allows your hands to react to solid objects as they would in real life, which means that, as you can see, your hands cannot go through objects, and if you try to do that, the object will be pushed. And it also allows you to grab objects, and what's interesting is that your hand will adapt to natural poses around the object that you're grabbing. There's only one caveat that I need to talk about, is that, as you can see, the very but the developer that is working on this physics ends has recently published, when I say recently, it's since Monday, published an improved script from Unity that allows you to turn any non-convex colliders into a set of convex colliders. That's why it works with the little ducky and other model that we have in our scene. Another feature that we want probably to use in our tracking preview is multi-device. So it's not really exactly XR specific, but it can be used to extend the range of your hand tracking. All you need to do is add more cameras, other cameras, and place them wherever you want, and then you need to document in your scene where they are placed. And from then on, you just have to drop a prefab, and this prefab will make what we call an aggregation of the data. It's not mandatory. It can be aggregated or non-aggregated. When say aggregated, it's mostly for one player, which wants to have a larger range of tracking. If you use non-aggregated, it might be more for multiplayer experiences, where you might want to have two people playing a mini game together, like Ping Pong or rock, paper, scissors, as it's called. We are currently working on different aggregation systems, so I'm going to show you a video of this. One of them is, for example, based on joint confidence value, and then we can just basically learn the joint position between the two sets of hands depending on the confidence value that we have from the different cameras. And we also document how you can write your own aggregation system. Small caveat is that it doesn't work with OpenXR yet. It's because the aggregation is made into the plugin. As soon as we find a very good aggregation system that will work in many cases, we will probably include it into the core service, which will make it available in OpenXR. There is a few Twitter handles that I highly recommend you follow because they are the people that have been working on those exciting new features. And for example, you talk about the elbow extension. This has been worked by 03 Ramat here. So I highly recommend looking at those. They are posting regularly about the work doing here in but not with too much corporate twist. It's really sometimes going into the gritty details. So highly recommend. And finally, I think a plugin that is interesting to talk about, because we didn't create it, is the MRTK. So we work closely with Microsoft to add our hand tracking as an input profile in MRTK. There is one caveat, is that it doesn't run on HoloLens because we don't support yet Universal Windows Platform. So MRTK2 needs our Unity tracking plugin, but MRTK3 can now use OpenXR. I just noticed one thing I haven't said at the start of the presentation is that the QR code you can find on the slides will bring you to the link that is shown under it, which might make it easier to just go on the website. And we also have interest in others, game engine and languages. So for example, those are things that we don't really have resources to allocate on, but we have a very active technology watch on the subject. So if you are a developer in one of those and you want to work in collaboration with us, contact us. So first is the Godot engine, which I'm pretty sure is very well known in the room today. There is already an integration that is possible with OpenXR, especially since now Godot 4 is integrating OpenXR directly in its core, but I don't want to spoil it too much, since there will be a talk about Godot in the next 2 days. And I think that with the newest integration of .NET 6, we might also be able to more easily port some of the tools that we have developed for Unity, for example. Another thing that we're looking a lot into is WebXR. So the specs support hand tracking, but not all the browsers so far. And those that do are on closed platforms, like Edge on HoloLens or Oculus browser on Oculus Quest. So right now we're looking into what other browsers are doing, and especially WorldVicXR, which seems to be a great project. If anyone in the room is working with WorldVicXR and wants to integrate hand tracking, please contact us. We are very interested in it. And finally, it's mostly a flurry of logos, of languages and stuff, but we are really interested in all binding that might bring our hand tracking into different game engines. So I put Rust because recently someone published, it was 4 months ago, I think someone published a Rust binding, and we want to see now if it would work with Hotham, or I think the third room engine is made with Rust as well. We will be very interested to see if we can integrate into it. But it is fair to say that with the rise of OpenXR, a lot of it might be already solved. We suppose that as long as your game engine will support OpenXR and all the spec, then it should work out of the box with our hand tracking. So yeah, that's a lot of things that we're looking into it. But now it's also time to show what other stuff we have published. So we're gonna now have a look at other scripting software we have published around XR that might help you in your development.
Yeah, so this is a screenshot of our GitHub. So the Unity and Unreal plugins that Rodolphe mentioned are up there. They're Apache v2. Pull requests very welcome. But the way we work here is obviously we try to open source as much as we can, and as we're kind of going along, if we kind of have to make something just to help ourselves, and then there's no need to keep it secret, then we chuck it up here on our GitHub. So I've got 3 things to highlight here that I wanted to share with you. The first is Unity Dependency Toolkit made by Rory. Made by Craig. So earlier this year, we were refactoring the Unity plugin and trying to remove a lot of obsolete code and assets. and we found that we'd often get like broken references, and you know what it's like in Unity where it doesn't tell you what the thing was. So this asset goes through your Git history and finds out what the reference was, and allows you to fix things up or work out if it's fine just to delete it. So that was really handy, and yeah, that's available. Lets you discover, navigate, and analyze asset dependencies. The next one, Play Recorder. This was made by Rory. So a few years ago, we were doing some user testing, and we realized that it would be better to record what people are doing in VR in a way that wasn't just from like a static camera viewpoint, essentially. We wanted to be able to see what they were doing in 3D and like replay their actions, their motions with their hands, and also the effect they were having on the environment. So Play Recorder is a system that lets you record and play back Unity scenes in the editor. So here we can see a timeline. So we've sort of got a recording, we've marked specific events that are interesting to us in some way, and then we can easily kind of jump between them. And this was super useful for evaluating and analyzing the data that we were gathering from these user studies and getting a lot more out of them. And of course, with the recordings, we were also able to go back and look for new things that we spotted during that analysis as well. And last but not least, we have our XR keyboard. Do you want to talk about that?
Yeah, sure. So I'm kind of repetitive, but go check out our website. What you see on the side here is actually what is on our website. It's a full article about how we design our XR keyboard for Unity and how you might want to do it as well. Because we've been doing hand tracking for a decade right now. And one of the main areas of research here is obviously user research. So we want to see how we can use our hand tracking with input systems and how we can improve those input systems to work with our hand tracking. So of course, one of the things we had to try is to make an XR keyboard. And along the way, we learned a lot of things on how to design a keyboard, how not to design a keyboard as well, and how to make it usable or not, as you will see, with hand tracking in an XR setting. It is important to clear out the fact that it is not used for long prose because we expect that in the XR world, we'll probably be using voice chat and other systems like that. So we don't need to resort to using a keyboard. But it is perfectly usable for short strings and inputs. So if you might need, for example, to enter your username and password to enter a different metaverse, for example. Yeah, I don't know. It's also been designed to retain the original layouts and form factors of current existing desktop keyboards, so it feels more natural to users. But it's all about what you want to do with it. You can actually change everything. So we've had it. Let me show first what it looks like. If you read our article, it will go through all the things that we have, all the attention we have put on customization of this XR keyboard. So one thing you can do, for example, is define your own buttons. So we show an example of an emoji keyboard, for example. You can also create your own layout. For this, we have an example of a numpad. You can have accent support, which is very important if you want to have your application to be as inclusive as possible, because a lot of languages today are using accents. And we also show how you can attach it to your hand to be a keyboard that is always attached to you, or how to put it anywhere in space. And finally, some funny stuff. We're showing to you how to add odd behaviors and events on quick presses that might not make it very usable, but might make it very funny. So the first thing that you can see here is actually a Pac-Man keyboard. Each key is a little Pac-Man, and when you press it, it will hit your finger. It doesn't really hit your finger, but it will try. And I think this is really the best, is the frog keyboard. Yeah, you can see the user being very infuriated about this. It's basically a keyboard where every time you press a key, a frog will hit it. And yeah, there's no way to explain that, but it's absolutely unusable. But I think those kind of input system might be fun in a mini game, for example. And that's basically it for us. You can do a final summary.
Yeah, so I've just heard there might have been a bit of an echo, so sorry, had trouble hearing us at all. But yeah, just to summarize, tracking software for hand tracking is available from us and from others on hopefully whichever operating system you're using. OpenXR, we think it's the future of hand tracking in terms of APIs. So we're encouraging everyone to use it, and we are making that available via our own offerings. And also, we provide free and open source plugins for Unreal and Unity, and obviously with OpenXR support.
I think if you want to contact us, you can follow us or contact the company at Ultralib or at UltralibDevs on Twitter. You can also drop an email at hello@ultralib.com. I think we thank you for your attention. Sorry for the brain farts. It was my first talk in public. And thank you very much for your attention.
We also have, I think, 5 minutes left. If you have any questions.
Of course, questions.
Just need to work out how we are going to see or hear them. Should we unmute?
Thank you very much, guys. Can you hear me? Hello, guys. Can you hear me? Can you hear me, guys?
1 minute, we're still... Okay, it's unmuted.
And you can hear me, right?
Yes, I can.
All right. We will have, I will see if there is any question in the audience for you guys. If not, we have also the chat for remote questions. So tell me, people in here, if you have any questions. I'm looking through the chat.
Any questions?
We're just
even non-related to
going
it.
once. So we have one comment for you guys here.
Hey, Adam, it's Bryan. How's it going?
Hey,
Northstar. Really excited about WebXR. Very cool. Hope it happens. Let me know if you need help. That was it.
Thanks. Yeah, we'd love it to happen. Ideally with a browser that's actually available on the platform that we support.
Awesome. So Nova's asking when this will all be available in Rust.
When will all this be available in Rust? Good question. If I might answer. So the Rust binding that has been published recently hasn't been done by us. And to be honest, as much as I have a strong interest in Rust, and a lot of people in the company here, we're sort of overwhelmed with all the work we have to do on the Unreal and Unity plugin. I don't think we can start tackling it soon, actually. So there's absolutely, yeah. We don't have any roadmap on the Rust thing, but we're looking into it, and yeah, we're very open to collaboration. I think that's all I can say about it, actually.
I think ideally it would be done via OpenXR. So
yeah, exactly. That's what we're hoping. I mean, we put a lot of resource in work on making sure our OpenXR and layer works great, so that yeah, anything that includes OpenXR will just work out of the box.
All right, thank you so much. I think that's it for the audience question. There's nothing else on the channel, so thank you guys very much and have a good day. All right.
Thank you for having us.
Thank you for inviting us, Frederic.
All right, no worries. Cheers.
Cheers.
for building a mobile VR headset. My name is Tobias Alexandra Platen. I mostly just go by Tobias in the context of Libre-SOC. I usually use these names because there is another person who is known by Alex, and my pronouns are they, them. This talk is part of FOSS XR 2022. So first I'm going to do a quick introduction of the Libre-SOC project. We are doing a mobile SoC which doesn't need any binary blobs, so it will work with only Libre software, and even its design is free. I'm coming back to that later. It has lots of peripherals, including those standards such as I2C and many others, and it also has a video processing unit and a 3D GPU, so it can do modern graphics using Vulkan, and it is based on the Open Power ISA and its extension scalable vectors. It has been prototyped on an FPGA, and we have already done our first test ASIC tape out, and its microarchitecture is based on the CDC 6600, an early supercomputer, but we are of course not binary compatible. We just learned the way how the CDC 6600 did do multi-issue, and that is one important thing if you want to do GPU workloads. On the hardware side, the Libre-SOC project is designed using NMython, which is a Python-based domain-specific language. And the output of NMython is standard Verilog, which can be processed using users, for example, and users transforms it to other formats. For the ECP5, we use NextPNR and ECPProc, and we have also used Libre software for ASIC synthesis using Coriolis VLSI CAD tools, and that is all done again using Python scripting. Only for users we have TCL, but the preferred language of our community is Python, and we also have some C++ modules, for example, inside the Coriolis software VLSI, and we use QEMU, which is written in C, for the simulation of the Power 9 ISA. So I'm going to show the Libre-SOC project and some of its repositories first. Here we have the Libre-SOC homepage, and here we see, for example, the Libre-SOC is open hardware or Libre-friendly hardware, and here we, for example, Raptor Computing Systems, that is the company that makes the Talos 2, and I'm going to show how I use the Valve index with my Talos 2 at the end of this talk. So the Talos 2 is marketed as a secure machine, and it is also certified to respect your freedom. And for the current generation of GPUs, there is no one that respects your freedom. So again, the most promising candidate for a GPU that respects the user freedom is the Arctic Tern. So the Arctic Tern can be used as a plugin for the Talos 2, and it can be used as a VGA compatible controller, and it can also could also run over scalable vectors, but only at a very slow frequency. So we would have to do most of the rendering tasks on the host CPU because we only reach about about 50 megahertz on the FPGA. And on the software side, the Libre-SOC project will just implement the standard power ELLIXR, so it can run distributions which already support OpenPower, such as Debian, and now upcoming Triskel GNU Linux, which is being ported to OpenPower as a high priority project. Finally, we have also Mesa as a Vulkan driver that is not yet mainlined, and I probably work on that Vulkan driver next year. The GNU Binu tools is currently ported to SV so that we can assemble programs for our extended ISA. And then we would also need a shader compiler, which is usually implemented as a JIT compiler on top of LLVM, but one could use GCC JIT theoretically. And on the software side, we only have a simple bootloader that is coldboot.c. I'm going to show that. So cold boot, when it starts, it just reads the configuration registers. And after writing the configuration registers, it configures the low-level hardware, and once that's done, it just jumps to the Linux kernel. So first it has to initialize the RAM, which is then also used as graphics RAM. And once all peripherals are initialized, we load Linux from the internal flash memory and jump to the Linux kernel. And currently I'm unable to demonstrate, so that has worked on Verilator, and it already works on different FPGA boards, but not on the Orange Grab. So, and one example is shown on the homepage that it can be used for pocket drones, and in one example there is a pocket drone which uses the lighthouse positioning system, that is the Crazyfly, and they are using the same FPGA that is found in the Valve Index and its controllers for tracking. It is also supported by users like the ECP5, and it's supported since the end of 2015, and the same FPGA is used in the Talos 2, and they are in both cases, in the Talos 2 and in the crazy fly, the FPGA configuration that has to be loaded is free software, and you can build it with free software. I don't have one of those drones, but I'm interested in just the shield that I can mount to my VR ShineCon and then fit my own electronics with a display, a battery, and the Libre-SOC hardware into the VR ShineCon for a first test. Or until Libre-SOC is ready, I use another SoC that is working good with free software, such as those from Rockchip. And finally, I'm going to list the Power 9 compatible hardwares that I know verified. One of those which I ordered in the beginning of the year is the Slime VR full body tracking. Which currently only works with Steam VR. But I want to get it working with Monado too. So in Slime VR, they are just using IMUs and an Arduino. And at the end, they are showing Beat Saber, where I have prepared a clone that runs on Godot. So Slime VR is one example of the Power 9 compatible VR hardware and VR software. And the Slime VR server, for example, already runs on my Talos 2, but I'm still waiting for the Slime VR trackers to arrive. So I was unable to test, and there is more work to integrate that with Monado. I also have a Valve Index HMD here. And its controllers. And the Valve Index is, of course, supported by the Power 9. If you have a good graphics card, or without a graphics card, you can still do headless VR, so you can use the Valve Index with the race-speed graphics using Godot 3, but you are really limited to headless because there's no way to drive the Valve Index without a display port, which the Talos 2 doesn't have, and Vulkan doesn't work at the moment either. So I'm using a Radeon graphics card here. You can also use a Wii remote and nunchuck. They are connected to I2C. The same interface will be also part of the Libre-SOC, as it is included in every type of SOC. We also will include a UART, so we can connect the bittrace shield, which I have been shown before, and it is also possible to connect the nunchuck to a Slime VR tracker, and you have a standalone VR controller that will work with a mobile Godot native VR solution, but that's still much work to do. Also, the HTC Vive and Tundra trackers are supported. They are similar to Slime VR, but I also include those optical trackings using the photodiodes, the same method that the bittrace uses. So I'm not going to buy those and probably connect the cape to a Slime VR tracker and try to use that with LibSurvive. So I have a Survive compatible VR data to LibSurvive, and there's also the webcam which can be used for April tag. So if you have a webcam and printed out some April tags, they are similar to QR codes, you can use the webcam for full body tracking in VR, but that's not giving the same good results as Slime VR does. And if you want to have better results, you would have to invest in additional receivers for the lighthouse signal. And if you have a Kinect, then you can also use scale track, but I never use that. There have been some videos how to use Miku Dance or nowadays VR chat with a Kinect, but I am not able to reproduce that because I can't use the Kinect that way, and I have been even unable to compile scale track from source. That seems to be unmaintained. They are also using GFreeNect, but probably if someone starts maintaining scale track again, I could use my Kinect again. So it has worked some years ago, and at the moment it doesn't, but or it doesn't work for VR, but I can use the Kinect hardware and get a picture on the screen that comes from the Kinect camera, including the dev's camera. And what does not work with the Power 9 are, for example, the Oculus devices, and I'm not sure on Windows mixed reality devices, as they need a powerful PC, and that PC does not have to run Windows. But I strongly prefer headsets that use the lighthouse tracking method, which has been developed by Valve and HTC, and the lighthouse tracking system is probably the most accurate, and it does not eat much processing power, so it's probably the best. And without SteamVR, there is no way to stream to the Oculus Quest from a Power 9 based computer. So I strongly recommend not buying the Oculus Quest if you want to have a Libre VR experiment. For this reason, I have investigated whether it is possible to build a freedom respecting using the Libre-SOC and not trying to port post-market OS to the Oculus Quest. The Oculus Quest has been jailbroken, but that solution is not good enough for me. So I want GNU Linux on smartphones such as the Libre M5, which I'm also going to use for the first prototype. So I'm putting the Libre M5 when I get it into my VR ShineCon, and then using the VR ShineCon, I could play simple VR games such as Neverball and probably also Godot Beep Saber, as that does not depend on high-end hardware. And for mobile VR hardware, I would have to then probably start with the PowerPi once it comes out, and then use the MIPI display, which I already had, and drive that using the PowerPi. And so I built a VR headset prototype once the PowerPi exists. Here I'm going to show the PowerPi specifications. And that PowerPi will come many years after the first SoC which we have tape out. So that PowerPi will be a bit more expensive in the development, and it would be sold as cheap units, so much cheaper than the Talos 2. And mid and low end graphics card, or even a version that supports high end graphics up to 4K, so that is high end mobile graphics, usually the same resolution that the ROC chip processor has. And those components will be very expensive, so it is important to have funding, and then it will take some time until a PowerPi that is proposed here comes available. If PowerPi comes available, I'm going probably to use that. Before the PowerPi, we have taped out a first ASIC, so that's described here. And many of those things work, so these are the generated graphics from the Libre software VLSI. And the first test chip is already working. But that is, of course, not something that is commercially available. And the whole project, which I'm doing, has been inspired here from CNLaw's Wireless 5, which runs Spreadgen, a small VR. So this is a large YouTube live stream. I'm not going to show that. So this looks like this. It has a battery, an Orange Pi, an adapter for Wi-Fi, and a USB hub, and the Vive is driven by that Orange Pi, and there is a special power supply, so it drives both the Orange Pi with 5 volts and the Vive with 12 volts. So that shows that wireless VR is possible even using GNU Linux, and that you don't need those commercial wireless adapters for the Vive or the Valve Index that only work on Windows. And the mobile VR headset would of course be independent, so independently usable. So you don't need a PC. You can just use a mobile device, or even it would be even possible to design a smartphone or a mobile media player that has the dimensions of a smartphone. So using a touchscreen and a battery, but without a modem, using Libre-SOC and probably using a higher resolution display than the Libre M5 had, because the Libre-SOC would be able to drive higher resolution displays. So I'm expecting that for mobile VR hardware that it has a high-end display. And for building my own mobile VR headset before the PowerPi comes available, I'm going to use SBCs from Allwinner or Rockchip. I strongly prefer Rockchip. And for the prototype, I think I can run Godot on it. So I don't have a PinePhone Pro. But there is Rock Pro 64, I think. and that could drive a MIPI display, and it could be connected to the bit trace shield. So I'm using a display and a tracking board for the shine cone, and I probably mount the SPC on the back of my head on the VR shine cone so that weight is balanced. I connect to the PC using Monado, using a Wi-Fi adapter, and I only use low bandwidth, so I want to do all rendering on the mobile device itself. And in the future, of course, we would be using Libre-SOC hardware and also using open hardware once open Wi-Fi hardware becomes available. That is currently prototyped on Xilinx FPGAs, but if enough investment is made, somebody might do an open Wi-Fi chip that is even fast, but I think that is even much more in the future, and I don't know when this becomes reality. And so I'm going to show how to use the Libre-SOC as a part for a VR HMD, the current FPGA prototypes, including that runs on the most expensive FPGA board from Raptor.js, the Arctic Turn, that is too slow at 50 megahertz, so an ASIC will be needed. But once we have an ASIC, I think that would be much cheaper, at least if those ASICs are mass produced. And that is also incomplete, as there is no GPU support in the Arctic Turn. And so that needs additional funding, and we also need FICE for DisplayPort to drive, for example, a Valve Index, MIPI to drive a display locally, and camera ports. The scalable vectors for the power ISA are still work in progress, and 22 nanometer power Pi needs other interfaces. I have shortly listed them, so that's now the end. I'm going to show a quick demo using my Valve Index. So now on my second presentator screen, I have shared here and if I move those controllers, the sabers move, but their orientation is still wrong. And I also have an example using OpenXR and Godot 4. So I have a small Python script here which acts as a launcher for VR games that first tries to find the Valve Index, checks whether the two controllers are available, and if both are available, then it I'm just showing that here on. I don't have a good. I have also done a short, less than 5 minutes pre-recorded thing using OBS Studio, where I just showing Godot gameplay using my Valve Index on the Talos 2. So I'm soon going to post that link. So that's now the end. Any questions?
Thank you very much, Tobias. Can you hear me now?
Yes, I can hear you.
So I'm waiting for some questions in the audience. Also checking online. If there is any questions, please feel free to send them in the chat. So we don't have any questions, but that talk was really interesting. Thank you very much for your time. You hear me, right?
Yes, I do.
So, Tobias, thanks a lot, just in time. And so we'll catch up later. Thank you very much for now.
So I'm now doing the end, and here I'm showing the.
Oh, you have a demo, right?
Yes, I have a
Okay. So
pre-recorded.
let's just finish the talk on that demo. I'll let you give you the mic now. Thank you.
Here I have I posted it on the chat. So that is a short demo that I have prepared, and I can also show live it on my second computer, which is VR ready. So now here.
So let's do that, Tobias. Let's use that second computer for showing the demo live here.
Yes, now it works. So.
All right.
That is the demo.
We can see it. Thanks.
And now here I have a Valve Index, and if I move that, it's a bit slow on YouTube. If I move that Valve Index, and it also has hand tracking, so the Valve Index is really one of the best VR headsets for use with Monado. You can also use an HTC Vive headset or a PSVR, but for me, I have chosen the Valve Index because it is using the second generation Lighthouse protocol, and I also have Beep Saber here, which is using Godot 3, not Godot 4.
Thank you, Tobias. We are running out of time.
So I'm stopping and then showing Beep Saber at a later time when it's ready.
Let's catch up on Beat Saber later.
So
yes.
Yes, because the game is not ready, so I have been coding today, and so I'm going to share Beep Saber, not Beat Saber, so that is a clone using Godot 3, not the original game. I can't run the original game. So I'm showing that probably later once I have Slime VR trackers and I have completed working on the software.
All right, let's catch up on this later. Thank you very much for now. And we'll go with the next presenter now. Thank you. See you.
Awesome. Hey everyone, I'm Bryan Brown from Project Northstar. Very cool being here in person and meeting a ton of Northstar folks who I've been working with for the past 4 years or so, finally getting to meet people in person. Very, very fun. And today I'll be giving a talk about the Project Northstar Foundation, which is a nonprofit dedicated to building open source spatial computing, which is super, super exciting. So let's get started. A bit of background on Northstar if you're not familiar. So Northstar is an open source augmented reality headset that was started by Leap Motion, now Ultraleap, in 2018. It provides a high resolution, wide field of view headset that you can 3D print and essentially build in your house or garage, as most people have done. So in the video there on the slide is just showing the view through the actual lens of the headset. So it's real, you can build it today, and you can even buy parts. It's super fun. And we've been working on this since 2018, so about 4 years now, which is super exciting. And there have been many, many different permutations and variations of it built by the community, some of which you can see here today at FOSS. There's actually a ton of headsets here, which is super exciting. Some of the photos on this page are actually from the Reality Hack in 2020. This was at MIT right before the pandemic, about 3 weeks before, so good timing on that. But it was really, really neat being able to showcase the Northstar headset right next to the HoloLens and Magic Leap and see people actually react positively to something that we had essentially hand assembled, which is pretty cool. But getting into it, why do we need a foundation for open source? spatial computing. And the main reason, right, in our sort of driving statement is that the future of spatial computing deserves to be open, right? We've seen a lot of companies right now who are in the XR space essentially fund it through other means, right? And billions and billions of dollars. And these devices right now are still very, very expensive, right? Out of the reach of most consumers and even most developers. You know, $3,500, $2,200, like $400 extra if you wear glasses and need an eyeglass insert. And what got me into Northstar in the first place was I really wanted to build a headset for cheaper than Magic Leap's prescription insert. And I think we're going to be able to achieve that, which is exciting. So the Project Northstar Foundation exists for a few different goals. Users deserve to have agency over their computers, right? Especially with all of the cameras and tracking information that these headsets are going to be able to gather, right? They're going to be able to see your room layout, the square footage of your house, what objects are in your house, what items you have, what things you purchase. There's so many different points of data these things will be able to detect, and users deserve to have agency over that. Users should also be able to afford these things, right? We've seen with mobile phones and smartphones how everything is locked down and increasingly more and more expensive and out of reach of most consumers. In addition, people should be able to repair their devices. This is true even of yesterday. I actually had to drive from Baltimore to Philadelphia to get a repair piece for my headset. And just goes to show the power of community and everything. And users should also be able to access their computers. And essentially what this means is they should be able to see everything their computer is doing. And in this case, headsets, you know, will be and are computers. So how do we build an open source ecosystem for hardware and software, right? If you haven't noticed, hardware is kind of expensive. It's sort of hard to build. And so the idea we have is actually to build a global distributed advertising and social network that affects elections and generally contributes to chaos. Pretty good thing. It has a track record. And actually, I'm just completely kidding. That's a joke. We're going to launch a nonprofit. So that's what we're going to do. So the Project Northstar Foundation is actually a nonprofit organization we started earlier this year. It has 4 core pillars: hardware, software, education, and then grants. So these are the 4 pillars we've identified as necessary for actually making the open source spatial computing ecosystem possible. And we'll get into that. So let's start with hardware. First off, hardware is very, very expensive, especially at low volumes. When we first started trying to replicate what Leap Motion had built with Northstar, the optics for the headset cost over thousands of dollars to diamond mold. We were trying to 3D print them, you know, find all these exotic methods for manufacturing. None of them were quite what you need for an actual optics system. So it turns out the way to do that is with injection molding, which costs a lot of money. And luckily, we've had a few members who have been able to fund that. And we've actually had you know, multiple runs of injection molds for optics. We've been able to buy displays at some volume, you know, usually 500,000 pieces or so. But to really build out an ecosystem, you need to essentially have a much larger volume and more buying power. So having a foundation allows us to achieve actually being able to interact with some of these organizations and companies who typically wouldn't even respond to our emails normally. Believe it or not, if you email people asking for 20 parts, they just don't respond. Typically, they want thousands. So especially with Northstar, there's a few different components that make an XR headset accessible and actually decent. And one of those is resolution, right? So typically, you're going to want at least 1440p per eye, which requires, you know, a high refresh rate as well, so 90 to 120 hertz, which means you're essentially delivering about 80 gigabytes of pixel data per second to the displays, which turns out you just can't do with off-the-shelf hardware, and you need to build your own stuff. And that's a lot of what the cost for Northstar has been, is building out custom driver boards, custom electronics, custom optics, and then with that, we're also combining it with off-the-shelf parts like the Leap Motion controller and SLAM sensors from Lexonis that'll allow us to solve certain problems, but not all of them all at the same time. So for how we're distributing funding through the organization, hardware is definitely our core pillar right now. This is what's going to allow us to purchase and buy manufacturing equipment, purchase molds, and keep the cost of components down for end users. You know, typically injection molds cost tens of thousands of dollars. And if we were actually trying to make a return on investment on that, we would be selling headsets for $2,500, which is not our goal, right? We want to make sure these things are at least under $1,000, if not under $500. So the next pillar is software. We want to be able to pay developers for their time. Wild concept, right? We're all here at free open source XR. It's free, but turns out people need money in order to live. And with the foundation, we really want to be able to pay these developers, some of whom are here, and be able to actually make their work profitable for them, and pay them for their time, which is super, super valuable. There's so much work that's gone into Northstar right now that's unpaid, including myself. I haven't received $1 for any of my work on this yet. And I think with while that's really great and exciting to see, we want this project to be sustainable for people to participate in. The third pillar is education, and this is super important. So a bit of background on myself, since I skipped over that in the beginning. I actually have a degree in architecture for buildings, right? No computer science, none of that. Everything I learned with Northstar, I learned by being in the Northstar community and just pestering people about what a MIPI lane is. And that kind of information just isn't out there, right? You could Google it for days and still not know what you're doing. So being able to have access to people or experts who actually know what they're talking about and what they're doing, and actually being able to work with engineers is super, super important. So a key part of the foundation is going to be building out these resources to make understanding what's actually going on in your computers or on your headsets more available and accessible to folks. That includes videos, documents. We have a great docs site right now called docs.projectnorthstar.org if you want to learn about how the headset currently works. And we're going to be continuing to build out those resources over the next few years with more and more engineering stuff, soldering, all of that fun content. And then finally, there's grants. Now, this is a platform we're still building out. But essentially, we want to have a grant program specifically for free open source XR projects. So things that are out there that aren't Northstar, but still contribute to the ecosystem. And we've seen so many different projects actually contribute back into Northstar from various areas, like Monado, for example, which is the open source XR runtime developed by Collabora, is currently one of the best ways to get into Northstar from a software perspective. And that is not developed by us directly, right? So there's a lot of collaboration that'll need to go on. So we're building out a grant system that'll allow us to help fund and build out those projects. So let's take a bit of a U-turn here and talk about the next version of Northstar. So for those of you who are familiar, right now we've got a version of Northstar that's pretty good, but we want to make it better. It's a bit expensive right now, especially due to some challenges we've run into with the chip shortage. So one of the projects we're working on, and this is work being done by Noah Zirkin, the co-founder of the foundation, is a low-cost driver board. So what this is going to allow us to do is essentially drive the same high-quality panels that we're using, which are actually the same ones in the Valve Index headset, at a much, much lower cost than the current driver board we have. Currently, the existing driver board for Northstar costs around $80 USD, which is a huge portion of a headset, especially if you want to get that headset down to around $400 or so. And this one we're aiming to have at a much, much lower cost, which will be TBD once we figure out all of the bill of materials and everything and get everything sourced. But it should be much, much more affordable, which is exciting. As you can see here, we're also experimenting with different SLAM solutions. So one of the most expensive parts of a headset is cameras. And even the Leap Motion, which we are including in all of our reference designs since they originally open sourced the project, is still one of the most expensive parts of the headset. So we've been experimenting with different solutions for simultaneous localization and mapping, or SLAM, which will allow the headset to actually sense its position in space, do room mapping, and eventually get, hopefully, parity with things like the HoloLens or Magic Leap. So I did want to put a special thanks slide in here, mostly to Noah Zirkin and the folks at Collabora. One of the coolest things about sort of running the Northstar community for the past while has been seeing it actually go into getting people hired. So actually 2 contributors who are here, Charlton and Moses in the audience, are actually working at Collabora right now. And they, in part, got hired due to their contributions on Northstar. So great job. And then, of course, without Noah, we really wouldn't have a project to stand on. Noah's been absolutely instrumental in allowing us to source components, interact with vendors, build things, manufacture things. The man literally has a pick-and-place machine, which is a PCB building thing, in his apartment. And he's actually hand-assembling PCBs. And without his work, Northstar really wouldn't be able to exist. And of course, last but not least, thanks to Luxonis for continuing to have meetings with me. You know, it's really interesting seeing which companies actually want to talk to you about this stuff. And the team at Luxonis who make cameras and AI-based systems have been absolutely supporters of this project, and it's just been great to work with them. So at this point, I do want to say that we have a little list of contributors here. This is a small, incomplete list. There's so many more. And you know, without anyone's individual contributions here, Northstar really wouldn't be where it is today, and we wouldn't be talking about doing a foundation like this. And of course, we are looking for funding. So building open source spatial computing is a huge task. Hardware is very, very expensive to build and manufacture. And we're looking for partners, funding, individual contributions to really make that happen. So if you're interested in that, please shoot me an email at brian@projectnorthstar.org, or you can join our Discord and chat with our community there at northstar.wiki/discord. Short link. So at this point, I did want to open it up to questions. So if anyone has any questions they'd like to ask, or concerns, or just in general, cool open source stuff, go for it.
Thank you, Brian. We got a question here in the audience.
Okay. So what would you say the far future of display tech for Northstar looks like? Like, let's say like a couple of years. What's coming after the ellipsoidal reflectors?
Absolutely. I mean, that's a great question, right? So it really depends on where we want to put energy. So if we were set out to solve the entirety of XR all at once, we wouldn't have a headset, right? We wouldn't have something that works. We would just have like in-garage prototypes that sort of work, but don't have tracking, or don't have optics, or don't have this stuff. And with Northstar, I've always seen it as like the XR ecosystem is a puzzle, right? And what we can do is we can have these components and we can put them together and build something that works, and then gradually improve it over time. So I think as optics get smaller, they get much more complex. And I think working with partners who are building smaller optics, like AntVR or Serial, for example, could be a great way of continuing to build out this open platform while taking advantage of not having to build every single item ourselves, especially because optics are just inherently much more complex the smaller you go.
Thank you. We have another question in the audience.
So once we actually have all of these different puzzle pieces, though, where we have a system UI shell, we have the whole software stack, we have a compute unit, we have the headset, I guess, what do you see sort of like the end user like being able? Do you see them like being able to just purchase a whole Northstar, or, you know, fully assembled, ready, choice of operating system? What does it look like when this is ready for everyday people that aren't developers?
Great question. So that's actually a great point, because right now Northstars are kits that you have to build and assemble, which is great for learning. Do it. Please buy them. But you know, we do see assembled headsets being the future, especially since it would avoid having to have users calibrate their headsets and do a bunch of computer vision to actually make the headset all work together. That is one of the biggest pain points right now. And I think you know, as the project moves on and as we're able to actually, you know, have more folks to assemble these and build these out and build out the entire ecosystem in parts, and we get more of a complete puzzle, then we'll definitely be able to start shipping out actually fully assembled headsets that are ready for more mainstream developers, I would say.
Third question here for you.
Hello, Brian. I wanted to ask, how does this LAN tracking landscape looks like for Northstar at the moment, and what are your thoughts on that, and what systems are you planning to use, and things like that?
Absolutely. Great question. So for SLAM tracking in particular, we've been using a few off-the-shelf solutions. And it's interesting because we've outlasted 2 of them so far. So originally we were using the occipital structure core sensor. This was back in around 2018 or so, and they've since discontinued that sensor. So we shifted to the Intel RealSense T265, which is great because it provides just off-the-shelf SLAM directly in the camera module, which is super cool. That sensor has since been end-of-lifed by Intel. So we've been moving on from that. Right now, we're investigating a few sensors from companies like XVisio, which will be great for just allowing users to just plug it into their headset and have it work. But we're also looking into something a bit more custom with Luxonis camera modules that would allow us to have much more control over the actual camera setup and SLAM algorithms. So.
Sounds good. Another question here in the audience.
Yeah. Where can we purchase said kit?
Great question.
And have you thought about selling them like in bulk as educational tools?
Yeah, so selling things in bulk have always been a challenge, especially with the chip shortage. It's just been hard to get bulk stock going, but that'll definitely happen soon. Right now, you can buy them at sale or at ahead.io, which you can find on our Discord. You can currently buy kits there. You can also buy the display driver and parts from Confu Displays. But we're working on getting full kits out again into the world at a more affordable price. So.
Okay. Is there anyone in the audience with questions? I think there's one for you from a remote viewer.
Oh, cool.
So he's asking, are you going all the way with decentralized manufacturing? And if so, where are the current difficulties with that process?
Sure. So yeah, so we are manufacturing as pretty much everything that we can. So that's including the driver board and an integrator board that handles all of the USB traffic and power delivery. Right now, my partner Noah is actually building all of those, or co-founder Noah, and that is actually going pretty well. We're about to assemble about 2,000 pieces of that, which will include full kits that'll be available soon. There's always little things that come up here and there. But the general idea is that we can either work with partners to assemble this stuff because the hardware is open source, right? So manufacturing partners will be able to assemble and build their own kits, which is part of the appeal there. So if we get more and more traction, more people will build Northstars, and there'll be like a little inter-competition thing of building and making them more affordable. Which should be exciting. But manufacturing is definitely quite a challenge. We're working with a handful of factories for different components and are working on a new optical combiner mold as well, which will have screw holes in this one. So that's exciting. So you'll be able to assemble it directly into the headset, which is cool.
Very impressive. So I just want to wait like a few seconds for another question from our remote viewers. In the meantime, turning it to the audience. Is there anyone else with questions here? Yeah, we do have another question.
Yes.
So this one is for everybody else that is out there, because I already know quite a few of them, but can you describe a lot of the Northstar variations, the wacky things that people have done with their Northstars to like show off just how customizable this is and why it's special compared to every other headset?
Absolutely. I mean, I can bring one. Moses, do you want to bring yours up here? And we can take a look at the world's wackiest Northstar. As we can see, wheelie chairs are still the enemy of cables. So yeah, to answer the question, there have been a variety of Northstars. Actually, the first ones that were built after it was open sourced was in Japan, and they actually used Raspberry Pi displays and built them about 2 days after the original project was open sourced. Yeah, it was quite impressive. And so this headset here, which I'm showing a bit for the camera, is Moses' headset. And this one is probably the most custom Northstar that you could do, modeled mostly in Blender. Blender's great. It's open source.
Not ideal for cats.
Right. So Yeah, I mean, this is probably the most custom Northstar that's out there right now. It has a whole bunch of specific modifications that Moses made for them. And, in the past, my first Northstar was actually before we had electronics and components built. So what I did was I took apart a Samsung Odyssey Windows mixed reality headset and rebuilt it into a Northstar. And it mostly worked, which was cool. And there's been a few other variations of that as well, of people buying older, like top-down phone reflectors and rebuilding those with Northstar parts. It's been really interesting to see just the variety of what people will build and do with it.
A question from the audience, remote. I think we partly answered that one, but so that person's asking if it's possible for us to replace certain hardware or connect extra hardware components to Northstar. So I guess it's possible, but how easy or how hard in general it is?
Absolutely. That's definitely something you can do, and it's something we actively go out and support. Right now, we have a board we're calling the integrator board, which is a USB breakout board that allows you to plug in different peripherals at USB 3 speeds. So as long as your peripheral works within USB 3.0 and doesn't consume a ton of wattage, then you can plug it into a Northstar. And if it does consume more watts, you can just plug another cable into it. So there's really no limit to what you can put on a headset. Some people have even tried putting an Azure Connect on there, which I don't recommend. It's very heavy, but you can do it. So.
Awesome. There's another, quite a lot of questions. Another question here from the audience.
Hey, Bryan. Thanks. This is a great talk. Every time I hear you, I feel inspired. This is fantastic. I was wondering, have you worked with universities? You talked about education. That's a great goal. Would you be interested?
Yes, absolutely interested in that. We've talked a little bit with some folks like the Illinois Institute of Technology, Illinois University, and it's been exciting. We haven't formalized any direct relationship with a university yet. I would say the closest we've worked with the MIT VR and AR lab a little bit. They have a few headsets there. We got to work with them directly at the MIT Reality Hack in 2020, and I got to go up there again in 2022, which has been super exciting. And yeah, I think right now we haven't formalized any particular relationship with universities, but I think that area of research is definitely super exciting for us. So definitely open to it. Let's talk, yeah.
All right. I think that's it in the audience. I don't see any question remote. So Bryan, thanks for the amazing talk.
Thank you.
And talk to you later. Thanks.
Hello, everybody. My name is Jakob Bornecrantz. I have my contact details up here. And if you want to talk to me, these are stuff that I like talking about. And today, these are the topics I'm going to talk about. The talk is FOSS X.Org update. And these are sort of the main topic here. I want to reintroduce OpenXR, so to say, just to make sure that everybody knows about it. I think people do, but yeah, I put in there as well. I'm going to actually list a whole bunch of projects that I want to sort of highlight a little bit, and then give an update on Monado itself, and then wrap the whole thing up. I thought I'll start out just a little bit before going into it. So one thing that I see that I want to highlight is that AR and XR and everything VR should be useful for humans, and entertainment is also useful, but there's often some things that we who like technology sort of get lost in, we just see the technology and not the usefulness in it. One of the things that, so this picture is from Back to the Future, and actually in one of the movies, you can actually see that it has a heads-up display inside of those glasses. So that's pretty cool, and I really like this picture. That's why I'm including it. Yeah, so VR and AR should make things simpler for us, not just complicate things, but it can be simpler to make things, how we live, or just as a tool for people to use in their work and daily life. All right, just a little bit quick about OpenXR. OpenXR is an open standard. It's made by the Kronos groups. The Kronos groups provides a IP framework, which is a very fancy way of saying that the people that are working on it won't sue each other. And it also allows engineers to get down to business. It's a collaboration by companies, and the individuals from those companies. So, us, Valve, Epic, Unity, Facebook, Microsoft, and all the big players. But yeah, again, it's really to solve problems and work together. And as I said, it's a whole bunch of companies, that are working together. And sort of a before and after OpenXR. In the beginning, everybody had their own API, OpenVR, Oculus API, Wave from HTC, and all that stuff. And then, you can now with OpenXR, you can make an application that is portable between the platforms. And if it just wasn't clear, yeah, OpenXR is a good thing. So one thing that I like the most about OpenXR, and the sort of has the highest frictions among people, developers sometimes, is the action system. So instead of when you deal with inputs, instead of you ask for a status of the X button or something like that, you say that I have an action called teleport, and then you, as a program, say, suggest that bind this to an X button if you have this type of controller. So then allows the user to rebind that action. You can get a list of actions, and you can rebind it. It's not actually bound to a physical device as such. You can say an application can organize their actions in such a way so that you have like a gameplay actions and you have a sort of a menu actions, and the user can, for instance, say, normally a application all uses the X button for basically everything, but the user actually want to bind just the menu click to another button. But if the application doesn't give any context of what it does, they only can rebind like the X button, like all of those actions. But now, since we're separated in actions, we can now rebind like teleport to one thing and menu click to another thing, say if you had your hardware. And this is really great for accessibility, where you can have very unique hardware things, and like some actions can be, people using it can be quite hard. So that's why I like it. It's a contention point, but it's here to stay. And it allows you to bridge various hardware that are quite different. Especially like my favorite is the WinMR controller versus the PS Move controller, where the WinMR has almost no buttons and like a joystick and a touchpad per controller, where the PS Move have a whole bunch of buttons and like no joysticks. Oh, sorry. So what does it give us? As I highlighted before, it gives us portable applications. Lets you move, less friction moving between platforms. There will always be some friction. Yeah, and including different inputs, even though like the standard is sort of moving to have your controller have a few buttons and a joystick. But there's still like you can move between them. And it's also a way to fight wall gardens. Because like there's a lot of things, like usually a corporation will use like the API as a way to lock things in, example CUDA, and things like that. So the whole light in the room changes when it goes to a darker side. So a little bit short about some projects that I wanted to highlight. So we have, I didn't really know exactly how to group them, so this is my sort of best approach. So we have hardware and drivers. On the hardware side, we have Project Northstar that Bryan very graciously talked about. We also have similar VR. We have a product called LucidGloves, and I don't know exactly the relationship between OpenGloves and LucidVR. And there's a whole bunch of more. I missed a lot of projects, so I just tried to. These are the ones like I came up with on my mind. There's Monado and ILLIXR, and OpenHMD, which is sort of drivers and platforms-ish, you can say. Or OpenHMD is more just drivers. There's also LibSurvive, which provides tracking for lighthouse-based tracking systems. And then I want to highlight Basalt, which is what we are using in our SLAM systems. So what some of you have actually been able to demo. Some toolkits, apps, and miscellaneous. We have Lover, also made by one of our employees here at Collabora. We have Godot, StereoKit. So those are what I would call like toolkits or game engines or whatever, open source. I want to highlight OpenBrush as a cool application from Little Brush. Then I also highlight XR Desktop and Stardust, which is like desktop application, basically a new paradigm in desktop. So getting your desktop in XR. And ALVR/ALXR is remote rendering for XR. So that's a project that is quite interesting. And we have somebody who is on the Monado server who's working a lot on it. So he's made a ALXR client. So I just wanted to shout out those. And again, there's many more. Maybe actually send me, like if you know projects, just ping me on Element or Matrix or Discord or something like that. Yeah, so I can update this. But like, I think, I actually really wanted to talk to B about FOSS XR, just not on one project. And we have some of these have actually talks in FOSS XR. Or talks about them. Some of them have already happened, some of them will happen. Monado is now or soon. Yep. So a little bit about Monado and status. Again, I'm going to go slightly through what Monado is and then go into the status thing. So, like, how do we do XR? So I like this slide. It's very simple slide, but it's like sort of explains where things fit in. So you have your program, and you sort of have this platform of software, and then you have your hardware. Most people like see the platform and hardware as the same thing, but for the sake of explanation, I split them out. And Monado it's the platform or the thing that sits between the hardware and the program. So Monado provides the OpenXR API upwards. We have drivers and stuff like that. There's also a whole bunch of other software that's not in Monado that's also part of the platform, say like the graphics driver, the kernel, the camera hub driver, a whole bunch of things that goes into like the whole platform that you can run applications on. But again, this is for focusing on Monados. So zooming in and adding a little bit more complexity. So again, you have the application up on top of the program. It talks OpenXR. Internally inside of Monado, we have separate things out. So we have what we call the OpenXR state tracker, which tracks states and sort of translates things that the application wants. One of the biggest things is that it actually does the input mapping. So like handles all of that semantics. That's a part of that. We have a compositor, again, which is not to be confused by either XR desktop or Stardust or Wayland compositors or X.Org compositors. So mostly what the compositor does is takes the images that the application takes and turns that into something that the hardware can display in a good way. So that's its job. You have your driver, and then you have a bunch of platform code. The picture is more complex than what I had there. There's a whole bunch of libraries, the drivers, they talk to each other. The compositor is split up, and like it's even there's a loader involved, and there's even a lot more, even more than that. So simplified again, but yeah. So all of them are interconnected. And I'm not going to dive in too much. I'll just talk a little bit about them. So we have what I call like the platform code, which is sort of like integrates into the platform. Talks Bluetooth, HID or something like that. We have the state trackers, where we have biggest one is OpenXR, but we also have a SteamVR driver, so we allow to compile the components of Monado into like a SteamVR driver. The drivers, a whole bunch of them. We have the compositor, and then auxiliary, which is probably like by now the largest part, where we have all the tracking and a whole bunch of helper codes to just let us compile and build things easier. And a good thing is that like there's a lot of code inside of the helper libraries, so your drivers tend to be just like a pick things I want from Monado. And it's even the same for Monado itself. Like you can pick the pieces you want from Monado and like build your own runtime. So it's almost like a runtime construction kit. You might have noticed like some of the errors. There was a like XRT something underscore, and these are the XRT interfaces, which is sort of at the core of Monado, so to say. And so those are the interfaces between different components. That is sort of, that's sort of at the core of that. It's purely in C. It is not stable because like we know that we are going to get things wrong, and we need to be able to change it. Otherwise, like it's just going to have to, you know, we are going to have to keep legacy code around or like work around all things. That is the part of like the state tracker. You know, the OpenXR API is the stable one. It's going to have to deal with all of the old crafted legacy code. So status, we are fully supported on Linux and Android. We are getting, by the day, we just had a couple of, we just had a merge request open yesterday that actually brings in new functionality onto Windows. So we're it's actually actively being worked on. And so that's going to be almost up soon in par with the other platforms. So yeah, these are my ever-growing lines of code slide. There's a lot of it, and you can sort of track the growth of it. It's getting quite big now. The thing that I want to highlight, let's see if I can. Oh, never mind. Yeah, if you look at the driver part of it, those are quite small compared to the rest of it. I think our most complex driver is Vive, which handles quite a fair bit of hardware, and it's like the most used one, you know, even that can see. I actually updated these a week ago and had to redo it because we merged the Rift S driver. So now it grew the code and also like added another driver. So we have 30-ish drivers. Some of these are emulation drivers or helper drivers, but yeah, a lot of them are actually for hardware. Yes, as I mentioned, recent-ish developments. It was a long time coming for that. We haven't done a release in a long time, so we're gonna probably do that once we get back to civilization. But before that, yeah. So we have the new Rift-S driver made by Jan Schmidt and the WinMR driver also made by Jan Schmidt. We have integrated SLAM tracking and hand tracking. Moses is going to have a talk about hand tracking, and there's also a demo on SLAM and hand tracking here. As I said, Windows is getting up to par. We now have all of the major APIs supported, the 11, 12, Vulkan, and OpenGL. We have expanded the compute composition. This is important because on some hardware, we can't do preemption of GPU work while on graphics queue, so you need compute queue for that. That also has time warp. So preemption is really important if you have an application that is slow and hogs your GPU for several frames, and you need to be able to do the time warp and all of that stuff on the GPU. So, and we also have CI for all platforms. So now we are far better at not regressing things. I know Windows suffered from this for a while, but now actually thanks to Ryan, we have Windows support there as well. So some thoughts. Actually, I only have like one thoughts from here. So there's like I think there was sort of a shift in accessibility in VR during the time of when Oculus DK1 came out, and like sort of a new generation of projects blew up, and like there has been like this institutional thing inside of universities and like some really big companies that have access to VR, but never was really around. But now that VR, XR, and AR is more available to people, there's like this whole new generation of projects like, popping up. So that's quite exciting to see. But yeah, as always, this slide is quite old. I had this slide for a whole bunch of time. I think this is from FOSS 17 or something crazy like that, that this picture is taken of. My notes say here that we want to have we need to build like a community for FOSS XR, just like Mesa is like a community for open source graphics. But I think we're kind of already here. We have a community of FOSS XR people that do work like Northstar and like Monado, ILLIXR, and all of those that are working together. So yeah, I think like mission done on this one. Mission done on this one. And also, I just want to say, highlight, I work for Collabora and we are hiring. These are just a whole bunch of links. The slides are up, so you don't need to see them. Any questions, thoughts?
Thank you very much, Jakob, for this nice review. So we have a question here in the audience.
Hi. Yeah, I guess how do you make money as Collabora? What's your business model?
Okay. No, I thought of something better to say. No, so we do a software consultancy company. We try to make Monado as best as possible, but there's always area that can grow because it's a huge undertaking. So there are always people that say, oh, it doesn't work for us. Can you help us with this special thing that we have? Or like we need this feature, or we want to see direction, or like come help us. So that's sort of how we leverage Monado and make money. So yeah, we're programming for hire.
Thank you. I'm looking at the audience, see if there's any other question. There's none, but I believe, Jakob, you have another talk right after this one. So why not take 2-minute break, and we'll see you right after.
Sure.
Thanks a lot.
Hello again. So in this talk, I'm going to talk about frame timing and pacing in XR and show a whole bunch of charts. Again, these are my contact details. And if you want to talk to me about stuff, these are things I like to talk about. So a little bit about the topics I'm going to talk about. I'm going to go into sort of what is a frame in the context of XR, the tools that I use, show a whole bunch of graphs, and then wrap up a bit. Yeah. So a frame can sort of be split up in 2 or 3 parts. You have the CPU parts and the GPU parts. And on the CPU, you can also split that up into 2 parts where you have logic, where you do like your physics update or yeah, stuff like that, basically game logic, and where you draw things, which is where you sort of tell the GPU to do things. We can put this on a slide or on a line. So you have your CPU, your draw, and your GPU parts. Where I changed the logic into just CPU. So this is what basically a computer or a game does every X amount of time per second, depending on your refresh rate. So like 60, 20, 120, and so on and so on. But you can see like these are broken up in nice little chunks. So you can also put them in sort of waterfall. So you have your CPU work and your draw and then your GPU. It's almost like I had thought ahead, and like you can put these on different parts of the computer. So you have like one thread that does CPU work, and another thread that does drawing, and then another thread, the GPU does the work. And now you have a pipeline. So you have, and this is like parallelized, so which is good for throughput. There is like some sort of writing between here. So a lot of games like optimize for this. So like I know Unreal and Unity have basically 2 threads, like they have logic and then they have the drawing and then the GPU. And they optimize to put as much work on the GPU as possible. But one of the problems here is like you can see starting here, like from all the way from here to down here is basically the latency of the things that happen on the CPUs, like it grabs input on the state and everything, and that's your latency. So if you do this and like the extra work that needs to be done to like split this up, you increasing the latency at the cost of throughput. So like in XR versus like traditional gaming, which is a large driver behind it. You have this fight between like I want to have a whole bunch of high utilization of my GPU and like high throughput versus like adding a whole bunch of latency. So that's something that's sort of a thing that I want to highlight. So a little bit about the tools that I use to sort of understand and see where the problems happen and like benchmark essentially all of the pieces that goes into like a frame or like timing the pacing for that. So one of the best tools, or like the tools I mostly use the most, is Profeto. So this is like the UI part of it. So Profeto is a Google project. It's split up in a server and clients. It can do system tracing. I will show an example of that, where you can gather a whole bunch of data about the system. And it has a really fancy UI that is really nice. So you integrate your Profeto into your system or your software when you sort of add tracing calls to like show when things start and stop. Quick example. I will show more later on, but I just have this here. Like, so like most of this is like stuff that I integrate into Monado, and then it shows up here after running it and collecting the data. But I also have added recently, or like working on a branch actually, some homegrown scripts and integration into Monado that dumps data in slightly different forms and then are post-processed by Python after using it. And then I visualize it using a application or a framework called Bouquet. So now we get the exciting part of live demo. So yeah, this is exciting. So first, let me see. Let me explode everything. Oh, I need. So first, I'm going to open up the example trace and to show the system tracing level of it, because I didn't capture beforehand the system level. Let me do that. There's a lot of data that it has loaded. So this is overwhelming, and it's probably compressed to all hell on the stream. So sorry about that, but let me do this. So this is a Professor trace. It has traces a lot of stuff on a phone, Android specifically. And up here you can see this is a CPU core, and these are the processes that are actually running in it. I can zoom in, and we can sort of see Android process here. There you can. It has collected like which speed the different cores are in. So again, it's a whole bunch of data to sift through. There's a lot of it. I just want to show up, like, it can tell you a lot. You can also go into a process down here. So these are different processes that are running on the system. Some of these have integration into Profedo, for instance, Surferfinger. So I can zoom in. There we go. So this is one thread. This is a plain graph or a call trace or whatever you want to call it. So function all the way in there. Again, with the system integration in Profedo, you can see like the state of this thread. So it's running and pausing. You can zoom in even more. This is like the thing that I like the most. So you can see that the latency between the latency between when the thread was set to be able to be run by the system to it's actually starting to run, was 12.8 microseconds, or no microseconds. Yeah. So this is like a thread or a trace. It has a lot of data. So the traces that I collected tend to be not so much data, because like the file, it's huge to keep track of everything starting and stopping and stuff like that. So I have for less. So I'm going to go into something that for less data, more reasonable. So this is captured with on a short run of a Monado service and a one application. Like that. So there's a whole bunch of. So it does a whole bunch of stuff over and over again. Yeah. So this is the compositor timing and the compositor running inside of Monado. You can see it mostly sleeps. It wakes up and then displays something to the screen. Currently, this is a gray screen because there's no client connected. So you can see the time, the thing that actually does the work is, about 1.1 milliseconds is when it's actually doing any kind of work. And we can go further down, we can zoom in what it all does. So this is like part of the integration that I have added into Monado, so we can see like what it's doing. So what I want to highlight is here. So here we can see, if we go down to the client, so this is the client. It starts up somewhere around here, does some work, loads a whole bunch of things, and then starts calling the OpenXR functions. So we call waitFrame, and call waitFrame again. And then we have all of the calls inside of OpenXR. But what happened here? There's a whole bunch of stuff that goes on here. So on the application's first frame, all of a sudden we see the GPU taking far longer. So this takes about 1 milliseconds, and all of a sudden here the GPU work took 3.4-ish milliseconds. And that caused us, because these are when the present engine starts presenting to the GPU start actually sending data to the headset, it missed. And it missed all the way up to here. So it's sort of that's why so these are sort of a synthesized things that I've added myself. So that's sort of signifying that hey, you slipped a frame. And you can sort of see that it's probably something because like, oh hey, the client is starting now. So you can directly tell that I missed this frame probably because like the client was using GPU. And if you were paying attention when I loaded the file, it said GFX. So basically I was using the graphics queue, so I don't have preemption, and that's why I missed the frame. Probably assume quite well. Yep. So now I want to load something else. Compute. And again, there's a whole bunch of stuff that like there's a whole bunch of them doing the same thing over and over again. So you're like there's only the thing that is, you have to sort of see or highlight where the things are, and you can see even the compute pipeline misses frames during startup. That's because like there's probably some things that in the kernel and everything that makes things slow, like creating new buffers and stuff like that. But you can see here when we're starting up with the compute pipeline, we're not missing frame when the application starts up. Its frame is late because like it's expecting it to be completed here. But that's fine because like now we can preempt the GPU and we don't miss frames. And you can see and if you remember back to like the CPU drawing and GPU thing, you can see them being repeated here, even though some of them are really small. Like this thing is really small. Just not even 0.1 millisecond. So yeah, so that's fun. So that's Perfetto and what I can do from it. And again, it's really, really, really good to be able to correlate things that are happening. And you can see like we spent a bunch of work making sure that there were no CPU stalls. Like the CPU, the client CPU doesn't actually stall on like the GPU or anything like that. So there's no like stalls. So we can see all of the functions that are being called there are really, really small. And we are waiting on the GPU to like make sure that the work is done before we pass it into the compositor. But like the client goes on, even though all it does is sleep right afterward, but like it still gets returned. So above the files, the metrics that I'm going to show now is process, you start Monado in with a special flag, and then it puts out the metrics in a file. I'm not going to show running a a script in a terminal, like that's not so fun. But the shorts are the most fun part. So these are the metrics collected from a other run. These we can see. So yeah, that will have to do. So these are how long a certain operation takes. A very interesting pattern here that the GPU work seems to fluctuate a fair bit on the from the client, up and down, but like the CPU is basically nothing, and the draw, even the first frame really bad, and then it's like settles. And here we have the relative time to when we predicted that the GPU time should be done by the client. So this is when we want the GPU to be done, and when the various things happens. So you can sort of see that the latency between prediction and when it's predicting and when it's waking up here. So there's about a 4 millisecond latency to it's being done overall. So this is again relative to predicted sleeping time. And this is from the above was client, and this is the internal compositor. It's a little bit weird because like here it's not, the client isn't actually connected, so it's just drawing a gray screen, and for some reason this is taking a lot longer than actually drawing something, so I will have to investigate that. But yeah, didn't get so far. But again, the CPU takes almost no time. The GPU, the drawing actually takes some time because now here we have basically a very small command buffer that we make, and here we have a lot longer. So we actually have to do things so that adds things. But again, it's these two together is like not more than like 1 or 2 milliseconds. And again, the same relative things. And this was using the graphics pipeline. So here we are again. You can see we're switching from drawing the blank frame to drawing actually data from the clients. And hey, we're missing 2 frames here. So this is the relative to predicted present time. This is the predicted present time when we are actually presenting. We're hitting all the frames except when the client connects and there's something happening on the system. And you can also see like little variations here and everything. So and to tie it off, I actually have the trace for. So this is the trace for. I recorded both at the same time, and again we can see here that we missed here. So I think let me go back, and yeah. Excuse me. Speeding through. Yeah, these are just backups. Yeah, so wrapping up. There's some limitation. Yeah, there's some limitations in Profeto. Yeah, the way I do the drawing, they sometimes get confused. I didn't point it out, but yeah, it looks weird, and then it's like I can't read the thing because like you can't really. You basically call Profeto, say starting here and ending here, and if you like get the times wrong, it can't correlate starting and stopping. So like then it just like you get a completely broken chart after some time, which is annoying in the frame timing when you can have actually overlapping things. I am not a programmer, a Python programmer, so like the script I made is in Python, and it's, I could do a lot, but it was like, oh god, what am I doing? A lot of that stuff. So if you are a Python programmer and really like charts and making them pretty, send me a message and like want to help me out with that, and I'll show you the repository to make it better. because like yeah. So I think that's actually it. If there are any questions.
So much, Jakob. Thank you. We have just time for just one tiny question. There is one from the audience here.
Yeah, it's a very tiny question. That little sliver, that first thing you showed in, there's like waiting.
Which in the charts or in the graphs or?
In Perfetto, like the first thing you pointed out in Perfetto, where it's like waiting to process. I was just wondering, what does that tell you?
The sleep or
Yeah, thank you.
Oh yeah,
Person.
yeah. So that can actually show you. I don't have an example of it, but like sometime I saw that the IMU thread. Actually, we have an IMU thread. Yeah. So this thread was scheduled for like half a millisecond or something like that, and it hadn't woken up. And like then I looked at the rest of the CPU, what it was doing, it was completely full. So it just told us that the scheduler couldn't schedule that thread. So we probably need to increase the priority on that thread to solve that. And you can also see like so for instance in here. The thread will probably be running all the time here and then stop running here because we're waiting on the GPU, so the thread isn't running. There can be some of them here as well because when we call into the kernel, you can also see that. And Perfetto can also trace all of the syscalls, which again produces huge file and like overloads you with information. But sometimes you actually have to go through deep and to see what is going on.
Thank you, Jakob, for this really nice talk. And yeah.
Thank you.
Thank you. Yeah. So I work for Collabora currently, but what I'm here to talk about is Project Northstar. So Project Northstar is an open source augmented reality headset. It was presented here by Bryan earlier, but in summary, it is it's an open source AR headset. It was created by Leap Motion, now called Ultraleap. They wanted to have a headset that could they wanted to have a headset that they could use to build like the future of AR experiences rather than the present. And given the it's got a very large field of view. It's got a and it can be built by anyone for, well, so originally they said it was going to be $100 in bulk. Now it turns out as individuals that becomes quite difficult, and realistically it was going to be huge sums of money. But what happened then was a community formed, sort of saying, okay, well, in theory we all know that this can be relatively cheap, but in practice none of us individually can make it for below thousands of dollars. So maybe we can work together to make a headset that we can all use as a community. So and the promise that was given, oh wait, can I do the video here? Yeah, there we go. So this demo I think may have been used by Bryan earlier, but essentially the promise was a headset. Now they used their own tracking, their own hand tracking with this to demo it, but this sort of dream of like a large field of view headset that anyone could build, that was I think what united everyone in the community. So yeah, so I personally got involved with the community quite early on. Sort of got involved in the Discord early on, and I got some hardware from Noah, who we'll see a bit of later in the talk, and I started building things. I got that from Noah. I put together my own 3D printed portable PC thing that I could use with it, and I contributed some changes here. You can see that was the old calibration, and then there were some issues with the new calibration. I don't need to go into details, but you can see at the bottom here you've got smooth gradients, which is good. That means it works. Now, for this talk, I wanted to, rather than talking about my own involvement, which I've done a few things, but I wanted to put the focus on how the project has affected everyone else in the community as well. So I have talks from, or I've interviewed. Oh, sorry, I forgot to mention. Yes, through this community for myself, it got me in touch with the people at Collabora and that sort of thing, and I work there now. So that's really cool. But yes, I wanted to highlight the other people in the community and how it's affected them. So I'm going to start with Javin, or Uri Vinkur, I think, who's a long-standing member. And here we go. Oh, audio's muted. Of course. Give me a second. Oh, sorry. Need to make sure. Where's my mouse? I'm sorry. I haven't. Oh, there we go. Click. Pause. Unmute audio. Play.
Hi there, I'm Juraj. I'm studying software engineering at Slovak University of Technology in Bratislava. And ever since I started my PhD, I wanted to bring affordances of augmented reality into the software engineering. So we would be able to move from the traditional bento box IDEs and crazy 7-monitor setups to the extended development environment where you interact with a single monitor and you can anchor all the supportive visualization tools and materials within your physical workspace. Unfortunately, I still don't have anything cool to show you because when I started this project, I had zero experience with augmented reality and also I have zero knowledge from this domain. And I soon ran into the problems related to 6D tracking, latency issues, sensor alignment issues, distortion issues, and so on. And my focus basically immediately shifted from the demo application to the design and implementation of the calibration procedure, which will give me a perfectly calibrated headset and all information that would be required for automatic adjustment of rendering for the user. At the beginning of the project, I was pretty desperate, but luckily soon after the Project Northstar came out, cool community has been formed, and thanks to them, I was able to get all required parts and learn how to assemble my very first AR headset, how to customize it for my needs, and thanks to them, I also learned everything important needed to implement the customized procedure for the optical calibration. So basically how to get the distortion model, how to implement the renderer which applies this distortion model to the scene view, and how to automatically figure out offsets between the sensor which are on the headset. So in the end, hands, environment, virtual objects are all perfectly aligned and user get at least the suboptimal experience with zero adjustments. It took me like 3 years, but it was the best learning experience ever. And during 12 years at the university, I never willingly learned that much just because I really enjoy it. So yes, for me, the Project Northstar is the best learning experience of my life. Thank you. Bye-bye.
Okay, and then we have we have something from from Nova, who is here, is also speaking at this conference.
As for the Northstar community, there's a lot of stuff that has happened, so I guess I'll just try and go in chronological order. Northstar, when I initially found out about it, was through the Leap Motion videos. I'd had a Leap Motion device, the LMC, for years, since like 2014. So, you know, really early. I actually got it as a graduation present from junior high. And so this is back when I wanted to do Stardust, which, as a reminder, is basically 3D system user interface for XR. I had that idea a while ago, so I was developing it using the Leap Motion, really bad prototypes. And then I found the Northstar, the initial demo video where they showed off the really simple hand tracking demos, though, and of course, you know, the desk UI demo and such. And it was like, oh my goodness, this is perfect. I mean, it was pretty much perfect for what I wanted to do. And so I looked it up, and there just kind of wasn't any way to build it initially. So I ended up basically having to wait until the oh, I forget the name of that. It was the one using the Raspberry Pi displays. So my dad and I went down to the hackerspace, and we basically bought all of the tools and we assembled it, and it actually worked. And that was really cool. And about that time was when the Discord server was starting to actually be created, right? And so I sort of went on there, you know, and I talked to a bunch of the people. I found Bryan and Noah, Zirkin and such, though, and they were all really nice, of course. And that's sort of how I got into Northstar. I was starting to get 18 at this point, and I wanted to get out and get a job in XR doing stuff related to Stardust. So JC from the Discord server, it actually posted about job opportunities for Holos. And the funny thing was, I had actually already Googled if the name Holos was available for Stardust, because I didn't have a name for it at that point. And so I found them, right? And I thought, oh, that seems cool, but it's kind of like there's no way. But then JC posted about it in the Discord server, and of course I did the interview and I got in, and that was really cool. So just the fact that even not just the actual Northstar itself, but just the community and the fact that people can share XR news in that space, that's really especially great. And I think a little bit after that, though, was when I had explained Stardust to Noah Zirkin, and he sort of made a bunch of cool Northstars, but he made them for his birthday, and he actually gave a Northstar to me for his birthday. I don't even know why he did that, but I'm grateful. I really am. And so I actually used that Northstar, and I still have it. I basically, shipped the Theseus it to make it into a Deck X because it was the 3.1 at the time, but I still have it in a display case in the corner of my room. So because he gave me this, I was thinking, okay, you know what though? I tried the Unity demos on Windows, and I tried, I think I might have tried the Steam VR drivers as well, and I was just like, oh, you've got to be kidding me. This is so janky and messy, and it just doesn't work very well because, it had an extended display. It had the Unity itself do the distortion. It was kind of a mess, and of course, every single project had to be custom built for this. So I had discovered Monado by this point, and I was like, yeah, Monado is the perfect place to put this in. And so I actually took the Steam VR driver, many pieces of it, and I copied them, and I pasted them into Monado, and I glued other stuff together, and it didn't really have hand tracking by this point. I actually did integrate a part of the Ultraleap V2 drivers into Monado, but that's a bit later. And so a lot of the most recent progress of the Monado driver for Northstar has been done mainly by Moses, but that initial push, I think, really, really helps to get it done. Because yes, it was janky, it was a giant mess, but it actually worked with a ton of different demos. Like, you can still even run a lot of the stuff on it, and the nice thing is it took the regular old calibration files. You'd literally just drop your old 3D calibration file, I think, at the time, into it, and it would just fill it out for you. So that was really cool. And of course, we're going to MIT Reality Hack. I got to see Bryan and Noah in person. And they were just as friendly as on the Discord in real life, though. And I got to use a Northstar there. I got to create the initial version of the SUI, or the Spatial Universal Interaction System there, which, by the way, I'm still using that today, right? And the Northstar really did help to sort of, how do I put it? Because of its superior hand tracking, I was able to effectively create really amazing demos. I'm really, really glad that the entire Northstar community exists. It really is just the most open XR hardware project in existence. Community's open, super accepting, the hardware is open, software is fully open. You just can't beat it. Great community, great project, great everything. And so yeah. And the community is also really supportive of, Stardust and such stuff that's not directly related to the Northstar, but sort of adds to the Northstar experience. So, really glad about that.
That was cut down to half. Yeah. It says this slide didn't load. Wait. My mouse isn't moving. Why's my mouse not moving? Oh, is it? Oh, it's up there. I don't see anything changing on this screen. Huh. Okay, well, let me try. Yeah, it said parts of this slide didn't load. Reload. Show anyway. Oh. Well, we got. Wait. Show anyway? Oh, there we go.
Hi, my name is Moses. I'm an associate engineer at Collabora, working on Monado, the open source OpenXR runtime, and optical hand tracking for AR and VR. So Project Northstar was like the singular catalyst that got me working on all of this. I remember seeing the first demos of HoloLens back in 2015 and thinking, like, wow, this is going to take over the world, and I really want to make an open source clone of this. But I never really found a good way to act on that feeling. I wasn't focused enough on finding good enough hardware and software to start with, and I didn't know what I was doing yet. But then, like, 5 years after that, at the very start of the COVID lockdown, I saw this, I think it was a George Hawk live stream, where he held up this headset for like 1 second, and my brain instantly just went, holy shit, is that an AR headset that I can build at home? And it was. I ended up spending all of my savings on a 3D printer and a new computer and the parts for one of these headsets, and I built one, and, you know, I went on this big adventure trying to build the whole thing I had in mind. So I ended up hearing about Monado, the open source OpenXR runtime, and that Nova King had written the very start of a Northstar driver there. It was incomplete, but it gave me a really great basis to work from, and everything I've done started there, basically. I did a bunch of work on, like, Northstar's display distortion correction, where you have light coming from the screen, it bounces off the reflector and into your eye, and what you see gets really distorted because this mirror is concave. So you have to correct for that distortion so that it actually looks like real content in your eyes. I spent a really long time writing all this computer vision code to draw a pattern on the display, observe this pattern using calibrated cameras where your eyes would be, and characterizing this distortion, then writing code that undoes the distortion and sends it to Monado's compositor so that every single frame the distortion gets undone and it looks right. Then I think after that, in November-ish 2020, I made a driver for ultraleap hand tracking, which this headset is not running right now, but ultraleap hand tracking inside Monado so that I could actually like interact with content and actually do stuff. And I did a bunch of general work in and around Monado to get various applications and games working. Like, I did this demo of WebXR using some patches on WebKit, and then I got XR Desktop working hackily with Northstar. It works better now. And me and Nova got StereoKit working on Linux, and I'm still using that software like all the time. And then later we got Open Composite and a bunch of other apps and games working. So this has, at the very least, been a really good learning experience where I got to do actual computer vision working on the display distortion correction. I did a little bit of computer graphics, and I basically learned C and C++ by osmosis working on all these projects with a bunch of help from Nova King, Nick Klingensmith, all of the people from the Collabora XR team, and Bryan Brown and Noah Zirkin, and all these people giving me tips and pointers and helping me with things that I was confused on. I'm really grateful to them for basically giving me all this free education and free help, even though I was just like this hobbyist with nothing to offer. Then at some point I learned that, oh, Monado is actually being developed by Collabora, this company who makes money making open source software, and they want to hire me as an intern? And obviously I ended up taking it, and it turned into a real job that I'm still doing, and we've been doing some really cutting edge computer vision stuff here at Collabora with our SLAM and head tracking. And all of this cool work I get to do and all these friends I've made and really smart people I get to hang out with was kind of caused by my getting a Northstar and just starting somewhere and hacking on it. And I don't think anything else would have given me such a good experience with actually getting out there and just making stuff. As opposed to like sitting around and waiting for some billion-dollar companies to do it for me. And also this was like the perfect thing to do during lockdown. Like instead of being stuck at home with nothing to do and just getting depressed, I had like this amazing project to work on that took up all of my time. And it's overall been like a really amazing experience that really did change my life. And I'm really grateful to like everybody at Leap Motion who originally made it happen, and Noah Zirkin and Bryan and Damien who have kept it going, and everybody else who helped me along the way.
Yeah. And there's one more from the aforementioned Noah Zirkin.
Hi, I'm Noah, and Northstar, I would say, has impacted my life as much as anybody's. Right around the time that the project was open sourced, of course, I decided to build one. I'd been an AR, enthusiast for about a decade and had been trying to build wearable AR rigs for that long, starting with motion capture devices and so forth. So this has been my passion for a very long time. Northstar came along, and of course I said, well, I'm going to build one. And there was this not promise, but allusion to or mention of in one of the Leap Motion blog posts that ideally a Northstar could be built for about $100, but that wasn't really realistic or reasonable if you actually had to make one-offs of the lenses, the combiners. And so if people were going to make lenses that matched the quality of what was in the Leap Motion demos, they were going to have to have things milled and coated with some exotic coatings, and that obviously wasn't within reach for individuals. Now, I had come to Shenzhen, China, where I am now, to develop a wearable input device for controlling heads-up displays, actually, as part of a startup accelerator. And that had sort of stalled. I was working with a product development company on some other stuff, and that sort of left me, I happened to be well-positioned, well-situated, geographically to get an injection mold made and explore mass producing these combiners, basically to enable everyone else in the community to do this. So, to build this project for a lot less and still have the high quality optics. So I basically dumped all of the cash that I had on hand into getting an injection mold made for the combiners, without, and I was in over my head. It was without fully understanding the coding stack, without fluently being able to negotiate that coding stack and communicate it to the factory that I had making coding the combiners. And so it ended up being this really long and expensive learning process of getting things wrong, improving them, eventually getting things right. And the community was, I want to say, very supportive and understanding of that. So people purchased the original combiners that didn't have the right coding stack on them. And then I tried to do right by people by then heavily discounting the combiners when we did get the coding stack right, and so forth. Gestures like that also had the effect of convincing my partners here that I didn't have any interest in the project being profitable, when in fact I just wanted to keep people engaged and sort of loyal to the project. So that ended up ultimately leading to a lot of drama here. But yeah, in terms of effect on my life, it has literally been my North Star. I mean, it became my all-consuming mission to actually fulfill the promise of making this accessible to everybody. So I've also, I've been working on new versions of it and trying to modify it to use more recent commodity headgear that's, incorporate eye tracking to take advantage. So given all of, sorry, I digress, but given all of the work that that other members of the community are putting in, for instance, Jiraj Javan working on the eye tracking, which is something that I've really insisted is a necessity for the headset to be viable, because knowing eye position is necessary for the image rectification basically going on in the lenses. Having applied pressure for that to get done, of course, there's pressure on me to make good on having a production headset actually have the eye tracking in there. So trying to keep pace with the, both push the community and keep pace with the community, so that we're keeping up with one another, has been tough. There's yeah, but it's again been all consuming. One of the big breakthroughs was getting these single piece combiners made, and then my old partners have sort of run off with the injection mold for that, and so I'm in the process of getting new tooling made, so it's been an exercise in stubbornness as well, and a test of stick-to-itiveness. Right now, I'm actually attempting to mass produce the various parts, the electronics, here in my apartment. So just to give you an impression of how all-encompassing it is, and that's while simultaneously trying to develop a new display driver board. I'm solder stenciling the PCBs in my little home office, and then just got my Tilt 5 pack. So very, very exciting. Digression again. I now have a pick and place machine in my living room, where I have stockpiled all of the necessary components. So it continues to be an ongoing series of investments to try to get this done. I have also made a tremendous number of friends and connections, and this community at this point is something that I'm fully committed to, and so Northstar sort of became my life, and is something that I'm still hoping to have a big part in, making accessible to more people and keeping it available to people. And a big part of that is bringing costs down and leveraging what resources I can to do that.
Thank you very much, Charlton, for putting all this together. That was very inspiring.
Hello, everybody. So my name is Nova King. I am the creator of Stardust XR and the lead maintainer. So first, let's talk about where we are in 2D right now. So actually, it would be best if I could just put this on the main display. Is that possible? I can't see the slides. I can't see the slides because that TV isn't working. Yeah, I'm just gonna. Sorry. I'm not used to this. I'll figure it out. Right here. Yeah, I don't.
No, they're almost there.
I just forget.
It's at the bottom, I think. Very bottom. Oh, I don't know if you can because it's 4K.
I really just gotta figure out how to drag this thing. There we go. Hey everybody, sorry about that. We're back. I had to fix this because it's a KDE laptop and I'm not used to it. So, okay, let's do this over again. Hi, my name is Nova King. I'm the lead maintainer of the project called Stardust XR. The formal name is Stardust XR. Informally, I just call it Stardust. But yeah. So, to start off, let's just discuss where we are in general in computing, right? So currently, in order to get the most out of computing, you need multiple devices. Your desktop most likely won't be very good for touch, drawing, etc. Your phone won't be good for things that need large displays, like spreadsheets. And devices in the middle oftentimes just don't have very good support, especially tablets. It requires a lot of effort to make sure that your whole setup is incredibly ergonomic, though, right? Repetitive strain injury is a thing for people that use computers a lot, and it's really difficult. So, for more serious work, what's it called? Okay, sorry. For more serious work, you have a bigger computer that is more fixed and locked in place because you need bigger hardware, bigger interfaces, etc. And that becomes really, really difficult when you, for example, want to do on-site construction or CAD on an actual construction site, right? Our UIs are semi-intuitive. They work well enough, though, but it still requires a fairly big learning curve for somebody who hasn't used them before. It's hard to be transparent because of the UI, as mentioned. Okay, so huge thing. There's a division between what is a power user, somebody who knows how to get the most out of their system, and someone who is a normal user, which can basically do basic tasks. And that's really, really annoying. And it's kind of necessary because, again, the UI is incredibly flat. It's not the most intuitive, and it's difficult to make it intuitive, but I'll get into that later. If you want to do customization, you basically have to be a power user nowadays, right? We have lots of opportunities, but the UI just isn't set up to do it. So because every bit of this UI is hidden away, it becomes difficult for us to intuitively understand how our computers work. Again, why you need power users. And every single bit of computing that we have is in a bounded 2D space, except for XR, right? What I mean is that this laptop has a bounded screen size. You know, you can't keep going outside of the display, and it's two-dimensional. So what about XR? Well, in XR, currently most of our hardware and software is optimized for gaming, where you need one thing to be shown at a time, and that's it. Productivity on certain headsets like the Quest, you'll only get 3 2D apps at one time, and you get no 2D app store. Few system UIs for XR actually have what I call full compute, where you can actually do anything that you could do on a laptop or a desktop or hell, even a smartphone on them, because again, highly focused and optimized. The existing XR system UIs are incredibly simplistic. XR Desktop is certainly getting a lot better though, so that's good to see. But for now, they just don't have enough functionality to replace our smartphones or computers, or even be a viable device except for a glorified PDA. And so they're monolithic, right? One team of developers and designers create all of the system UI for them. This one is a big one. It's changing now, but earlier, like a few months ago, I would say that you're just flat out unable to develop XR inside of XR in an effective way. Simula VR has gotten a lot closer. XR Desktop has gotten a lot closer, right? Most UI just mimics Pancake UI entirely. It's because it's what people are used to. Controllers or hand tracking, pick your poison. Multimodal UIs are not very common, and when they are, they're very hard to get right. So what about this? This is where we could be. Your HMD could, in theory, do basically all of your computing, provided it had enough power in the back. That could be done through streaming, more efficient chips, whatever. I'm not going to go through every single point there, because it's pretty common knowledge, but for serious work, we could actually do that on HMD. And you could have potentially one HMD. You can just plug into different computing devices if you need more power. Of course, those computing devices may be more fixed in place, or you can still stream. Because of the 3D UI and because interaction design is further evolved, people can understand their computer like never before, right? Because instead of having a flat panel showing a bunch of text, you can have a virtual object that its shape indicates what is happening underneath. And again, I'll get into that. Accessibility through options. In 2D, there's only so much you can do inside of a tiny little square. In 3D, provided the proper hardware, you can make your entire world accessible. Here's some basic terminology. I'll sort of try and simplify it in the actual thing as well, but a display server is effectively a program that other programs connect to in order to handle the input and output. So 2D display server, for example, could take your touches, mouse input, etc., give them to the appropriate app that's focused, and then it could take all of your apps, put them inside of window decorations or the frames like the title bar, and then take all of that and output it to your display. Am I going too fast? Okay. System UI is my name for a desktop environment, generic across all things, because desktop environment is pretty Linux specific, but you still have system UIs for stuff like Android. I mean, it's literally called system UI. You have system UIs for Windows and Mac. All of the operating systems that have a GUI have a system UI. which is basically your display server plus essential apps and also system control. So those are the three things that make up a system UI or a desktop environment. A Wayland compositor is basically is a display server optimized for the next generation in Linux of 2D apps. So you can think of it that way. So this is my project, Stardust XR. It's a display server, and also it has its own custom protocol for XR system UI. It's very, very different than 2D display servers, which I'll get into. It enhances 2D and 3D content through 3D UI. This is something I haven't really seen happen yet. It requires a fairly high level of integration, which is why it's difficult to do on Android. But on Linux, it's a lot easier. You know, it's still complicated because it's a new medium, but right, so desktop environments. The concept of a desktop environment or system UI in traditional terms is usually one team of developers, right? They have a vision, as in, this is how I see people interacting with their software through my piece of software. But one potential issue with that is if they don't account for something, you either have to add that in afterward, which is often not easy to do. There's sometimes a plugin system, but that's not convenient. Or you have to switch all of your workflow over to a completely separate option, which is difficult. I've had a lot of difficulties. Yeah, so the functionality of Stardust is not hard-coded, right? The server, for example, the server is a component, and you can just launch other Stardust clients, and they'll instantly spawn in 3D objects that you can interact with, right? What Stardust is not. I've had a lot of confusion about this. Some people think that it's way too big a scope, and that's understandable. But first of all, I'm not trying to reinvent how 2D apps work. Wayland already does that very well. There's no cross-platform standard that I've found for 2D apps as of yet, unless you count web. I am not creating a platform or protocol for 3D non-immersive apps. You can think of those as like a calculator app that's just 3D and it's floating and you can move it around and you can put it right next to another app. Well, Stardust does have this capability. In theory, I would not recommend it, and all of its different architecture is specifically optimized for widgets, system UI, such as Wi-Fi control or UI to 2D and 3D content, and so on, right? I do not claim to be qualified to do all of that. Most of the reason why Stardust, I think, works and why it can be so flexible is because it only takes up a tiny piece of the whole XR stack. And then it is not a platform or protocol for immersive 3D apps. OpenXR does this very well. It's made by a bunch of people, far more than I'm guessing Stardust will have, but that's good because the more people, the more close to the use cases we can get. And again, plans for Stardust to actually incorporate OpenXR, whether that be through parts of Monado or so on. We'll see. Stardust is very specialized for XR. It does not do 2D very well, and I designed it that way on purpose because the inherent way that people interact with 3D and the real world differs highly from how we interact with 2D. 2D, I feel, was a compromise. It was something because of the limited technology of the time, but I think we can do better. You know, for example, 2D experiences and apps absolutely have their place, but in terms of the main interface to the computer, I think 3D is a really good option. Stardust is optimized for design, stability, and speed. Lots of other projects, though, like, for example, the Oculus Quest Home, they're difficult to design for, right? Because they don't take into account a lot of the affordances you need in XR, all of the different areas in real life you may be, because you have to interact with software on an airplane different than you would inside of a giant room, like with a giant whiteboard on the side, right? And it's difficult. I don't think that one team can really get all of those cases right, but I'm designing for that in Stardust, specifically because anybody can create a 3D object, right? Yeah, okay, limited scope, right? It only does system UI. I'm only targeting system UI. Please only do system UI with it. And it doesn't re-engineer any working pieces. OpenXR works really well. Monado works really, really well for drivers. You know, Wayland works well for 2D apps. I don't want to recreate any of those things because they work. But one of the areas I feel doesn't work is the way that the desktop environments or 2D, or display servers as a whole work, where one team of people creates an entire desktop. Okay, again, monolithic. You can just pick and choose virtual objects in Stardust. It's early days, so there aren't very many objects to choose from. Not many programs, but we're working on it. Okay, ergonomics. Because you can just take out objects at any time and you can interact with them in an intuitive manner, because Stardust gives the developer all the data they will need to expose it to the user. Because of that, it allows for great ergonomics. Okay, hot swappable UI, I covered that. Very easy install. Simula VR and XR Desktop are difficult to install, and that's because this is complicated software. I've tried to make it a point to make mine easy. Lightweight, yeah. This actually uses StereoKit, which is an upcoming talk, I believe, tomorrow. This uses StereoKit for all of its UI rendering. It's really great. You should check it out. And because of that, it's going to be very optimized, at least graphically, on mobile headsets, because that's what StereoKit was designed for. Here's what it can do now. And demos are coming, I promise. It can allow lots of other programs to completely remain separate, right? Separate in licensing, because the server is GPL, separate in execution, so you can launch it from anywhere, etc. And this means that independent teams of people can all make parts of the system UI. I use Monado as its backend, technically any OpenXR runtime, but I don't think anything but Monado implements the EGL extension, which is what I need. You can display 2D apps on different surfaces. So eventually, you're going to be able to have a virtual smartwatch where you can take your clock app or your weather app or whatever you want and just drop it on there, and now it's a virtual touchscreen or such. You can also manage the 3D interactions through the SUI, or the Spatial Universal Interaction System. I've worked really, really hard to create that because a fundamental problem is you have a bunch of inputs. You have hand tracking and controllers and pointers and so on. And you have a bunch of things that may want inputs. And because a bunch of different people are making these, there is no standard manager for that. So the SUI is an attempt to make all of that work together in a very seamless and intuitive way, even with completely different people unaware of each other's existence, creating different software. There's a bunch of things there, but I'm going to skip over it. 3D environments. You can be in any home space you want. It's always nice to have. I'm not going to go over this too much, but if you display server nerds want to take a look, feel free. Okay, so Stardust UI components. Stardust XR components. Server is the glue. Everything connects to the server. It's on top of OpenXR. Stardust-XR is basic standard so that everything can connect up properly according to the same socket. Fusion is a high-level library that gives you direct exposure to all of the objects of Stardust. Molecules is a higher-level UI toolkit similar to MRTK, very early in development, of course. Flatland is a bit of a joke. The name is a bit of a joke, and it is a way to interact with 2D applications inside of Stardust. Atmosphere is a home space client. And Gravity allows you to launch applications in a specific place in 3D space. That's another thing that really, really hugely differs, because in 2D, you can just place an application right in the center of the screen, and that'll work. In 3D, it's a bit more difficult. It's generally speaking in design, how to put this? It defeats object permanence when something pops into existence out of nowhere. This is some SUI code. I'm just showing off, basically, you can create an action, and this is really good for UI designers and developers. You can create an action that can contain anything you want, because it'll give you temporary access to the raw pose data of the hand and such whenever it's nearby the object. And then, using that, you can get the raw pose of that object again in order to create rich interactions. So I feel this is a good compromise between the stability and also, how do I put this? Stability and low scope, like not privacy leaking nature of OpenXR's input system, right, and input actions, but also in applications where you want raw data in order to provide very rich and natural interactions. So I've worked hard for that. Now it's time for the demos. Sorry about all of that. Okay. Let's see if this will work. So, all right, I have it on the other desktop. So let's first.
I want to launch Monado with it.
Yeah. Yeah, of course. Yeah. Okay. I'm in. So we launch Monado first. Is that working? I can't tell.
It kind of looks like the stage tracker didn't launch. Or it looks. Give the rest of it a try. It's probably fine.
Okay, sure. So this is the server, right? Okay.
Oh no, it definitely didn't launch. If you don't get if you didn't get the white screen, it definitely didn't.
Yeah. Worst case scenario, I do have some videos for some of the demos on the old version. I forgot to mention, but I'm rewriting this in Rust for stability reasons, because it's a display server. If it crashes your whole system UI, you can't use the device without it restarting. So.
I have no idea. Yeah, the graphics stack isn't launching. I can't tell you why.
Is it to do with the HDMI?
Probably. You should probably launch it in flat screen and just do that.
Okay, yeah. I have a flat screen testing mode for this. Trust me, it works in XR. That's all I'm gonna have to say for now. But okay, so first let's launch the server. So is that not? Oh, that's frozen too. Of course it is. Now it didn't draw window decorations. Yeah, this is demo syndrome. This is what always happens.
We only have some graphics.
Got any clues? Well, I can't control C. I think the whole KDE desktop might be broken. Oh, look at that. I can't. Yeah, we might have to. I feel bad. My talk is.
Absolutely no problem. So we'll just take like few minutes. We'll fix all that and be back. All right. So seems we could fix everything. It's back to you, Nova. Thanks.
Right. Now, now I just need to get the correct terminal up. Okay, we're back. So that's the Stardust server. Okay, CD Stardust XR server, and then I'm just going to go cargo run. This is not installable through cargo yet. As you can see, I've got hands. Oh, right, it's mirrored, I forgot. Okay, so I've got hands. These actually do line up in the viewport, but they might not to the camera fully. Oh, no, they do. Awesome. So by default, you get blank void in Stardust because, anyway, so now I'm going to launch Flatland, which is the 2D client that can create 3D UI for 2D panels. And it's all abstracted away, luckily. So that means that UI developers can make it without having to worry about all of the different Wayland stuff. So again, just simple as cargo run. Lots of these are also installable from the cargo crates.io repository. So you can literally go cargo install gravity or cargo install flatland, and it'll work. You've instantly got it installed to your system, and distro packages to follow. So I've got, oh yeah. So as you can see, I've got a flatland input window for 2D whenever I want to interact with it with ergonomics because it's early days. And I have no panels open because I haven't launched any Wayland apps. App launcher to follow. There's a lot of components here in anything. So, okay. So Wayland display equals Wayland 1 GQPA platform Wayland retro term and there we go. Oh, yep. So this is Flatland up and running. As you can see, all of the different panels, they are actually 2.5D. They have depths, right? So they have a unique wraparound effect using UVs. This is literally just a model. It's a scaled model that I called a method on to instantly apply the texture, the material of the window. So I can also take these, and if I am lucky, can grab them, right? And can move them around. Again, this is very basic demo, but you'll also see maybe, is the cursor deciding to work today? Oh, I think I disabled it for the demo purposes. This is not going to impress the ultra elite people because of my UI. Okay. Yeah, sure. Actually, I'm going to need to launch just a raw terminal for that because if I exit this one, it'll exit for good. So launch that terminal. And now, if I click inside of the Flatland input window, then I can move around. Is it working today? Oh, no. KDE, why you do this? Oh no, it's still running. Oh. Yeah, okay. No, typing will work. Typing will not work. It froze. Oh. Okay, the library I'm using for Flatland called winit breaks whenever you put the cursor out of bounds when it's not supposed to be. But I can just launch it again, which is really nice. Don't have to relaunch the entire thing. I only have to relaunch one component when it fails. Okay. And as you can see, oh, no, wait, you can't see. Okay, here, look. Pipes, page, and, oh, wait, pipe's not working. I can do pipes.sh at least. So. Oh, wait, hang on. I should make that full screen, shouldn't I? It's in a tiny little corner. Where's my cursor? Oh, Flatland caught it. Oh, I gotta change the keyboard shortcut. It does not like KDE. KDE does not like it when you do that. But yeah, so there's that. Now I want to show you another cool demo, which is called Gravity. Now, because we are in 3D, right? one of the principles of material design that I like best is that everything that pops up should come from somewhere, right? When you tap an app icon in 2D, it should appear that the app is flying out of it, right? Because then you instantly know what triggered the action, and it's a lot more intuitive of UI. This is especially true in 3D, where nothing literally just pops in front of you instantaneously. So, for that matter, I have the demo of Gravity, which can launch anything by popping it up in front of you in 3D space. But that's only because it's showing the underlying architecture that allows you to make app launchers. We can grab it out and place it down. I just didn't have time to make one. Oh, wait. So 0, 0.5, 0, /, target, debug, examples, spatial. Watch this. Doesn't. Oh, yes. I keep forgetting. It's not. I thought it was on the other view. So, by the way, this is a 1080p webcam. So as you can see, though, it just placed that 0.5 meters in front of where I started. So this already actually is about to be implemented in Atmosphere. So you can create just a simple TOML file that describes an environment and launch a Stardust application directly with the environment. So that is pretty neat. Now, and you can also, by the way, this is chainable. So you can literally use Gravity to launch a script, and then Gravity inside of that script to actually launch other things. So you can literally have a full setup instantaneously relative to your HMD in a matter of like milliseconds. So it's really good if you're like the kind of person who sets up i3 everything manual, because it'll work. Okay. So now we get on to Atmosphere. Is that right? No. Okay. So now I am, if I switch over, I am in the side quest. I'm in the side quest home space. Right? And so I can interact. Everything, by the way, planned is collisions. And also the ability to float around. Interesting thing about Stardust, you cannot move the person in Stardust. You can only move things around them. But due to zones and other components, that'll actually work across basically all of the applications. So, yeah. And then to show off just how easy it is to actually do things inside of Stardust as we are, I'm going to launch Flatland. I'm going to launch Flatland, and then inside of Flatland, I'm going to launch a terminal. Okay, that's a bug. It's not perfect software yet. And Flatland doesn't want to quit. Uh-oh. Oh, the cursor was just frozen for a bit. There we go. And now, if I go into here, I can go cargo, uninstall, Stardust, XR, Gravity. Right? And then I can literally just reinstall it, for example. That's not the delete key. Oh. Right? And then I can literally use Gravity straight inside of here. It gets a bit jittery whenever it's running I just need to increase the priority of threads on Monado to make that.
Keep your head still or it will die.
Oh, okay. I'm going to just tilt it slowly down so everybody can see. Thanks. Debug mode? No, I'm running debug. Wait, no, finished release for Gravity, but only Gravity is in release mode. Oh, installed. I should have guessed. And then so we can literally just do cd. I need to know what directory that is. Oh, it's in root. Oops. Yeah. And then Stardust XR. And then, of course, we can go Gravity 0.50, which will do 0.5 on the Y direction because it's following OpenXR convention. And then target, debug, examples, ghosting, fun. Or that's not ghosting, never mind. And spatial. So as you can see, it'll print out a bit of debug info. Where is it? It's up there. And so it's not grabbable yet, but. And so it's very basic demos right now, but I hope you can see that you can just program a simple Rust crate that can instantaneously create an element of system UI. Already, you can have control panels with buttons on them. You can create whole entire environments. Soon, you'll be able to create environments with wall clocks that actually work. Lots of cool stuff. And so I really want to make it to where spatial computing, the whole idea that you could do computing, that you could do basically anything you could do on a desktop or smartphone on an HMD, I want to make that a reality because it's more intuitive. It's a lot better for creativity. It actually, believe it or not, it would get people to actually go out and exercise more because, well, if you're working an office job, you have to stay in one spot unless you buy a fancy treadmill. There's a lot of different effects I think it could have on people. So as long as we make it trustworthy with FOSS XR, I think that's the best course of action for this new piece of technology. Thank you, everybody.
Thank you very much.
Oh, and you can try this out yourself. Go to stardustxr.org. Here, I will go over to the slides and I'll show you. Oh, wait, the slides are gone. Yeah, just go to stardustxr.org. You can find everything you need there, including how to install the server and Flatland so that you can try to begin with. Instructions on how to install and use Atmosphere and Gravity will be coming shortly, hopefully. And yeah. Discord, matrix server, all that. Thank you.
Thank you, Nova.
Moses Turner. For the record, this is my first conference presentation ever. I'm really happy to be here, but I'm also really nervous. So if I seem nervous, it's because I am. But we're going to get through this. This is going to be awesome. So, all right. This is me. Is this mic being inconsistent? Okay. And that's what I look like in VR. That's my preferred form. You can see I have a bunch of links. So besides optical hand tracking, I'm interested in a bunch of stuff. I am interested in transhumanism, like radical augmentations and life extension, and I spend a lot of time in VR. And then I'm very, very, very interested in machine learning and AI and computer vision and math and obviously free and open source software. And then if you're interested in joining Collabora, you can ask me or anybody else. So, all right. So the first part of this is why do I care so much about optical hand tracking? Why has Collabora been paying me for like a year and a half to do this? So some people know this. Basically, you can't use controllers at the same time as a keyboard. Like, you have something on your hand, but you want your hand to be right on the keyboard. So if you're typing a lot, controller-based VR apps do not work very well. So you have to be, without hand tracking, you'd have to be okay with just like 3-DOF head input, which isn't much. And then it's markerless. You don't need anything besides a headset on your head or external cameras somewhere. And then it has a lot of advantages for accessibility because, again, it's always there. You don't need anything else. It is generally easier to emulate hand track gestures using weird input devices than it is to emulate input devices using hand tracking gestures. So for people that like don't have hands or are missing fingers or stuff, you can make special input devices for them that solve their problems while using one interface, which is your hand. And even so, markerless optical hand tracking, it often just doesn't care about a lot of problems. So that's the main motivation. We want to do stuff in VR. We want to not just play games, we want to do stuff. We want to write code, we want to design stuff. We want to make the world better, and we need our hands. So this has already been proven out. You can see MediaPipe, Oculus Quest, Ultraleap, HTC. A lot of people do it. It already seems to work really well. And then another cool thing is that for people who live in VR, it can feel a lot more like it's your hands. Like you can do stuff and it's your hands. So like again, controllers are good for games, but this is a lot more for not games, which is, yeah, that's our thing. So then why am I working on hand tracking? Like, is there really no prior art that's good enough? So we have MediaPipe. I honestly think it's pretty good. I have some minor complaints, but the main thing is that the dataset isn't published. So if you need to fix problems in it, you have to get the dataset from them, which is hard to do. And getting commercial licenses for datasets is really hard. So everything is research only, which means it's hard to take this and have it actually have a good impact on people's lives. So basically, for one, I'm just trying to make good hand tracking, and for two, I'm also trying to publish like a lot of data sets and code and materials you can use to make your own hand tracking that have totally free licenses, and you can use them for anything you want. And hopefully this will push the state of the art forward and also lower the barrier for other people to actually get into it. So some of these are retroactive, but these were kind of my main goals at a super high level. Like, again, we want something that already works that you can just use. We have that, it works, it's there. And then publishing all the data sets we've collected. This will happen very soon. This isn't really even a problem. And then same thing for our synthetic data set. Again, going to happen soon. We mainly have to figure out how to get really good scans of people's hands. Not either from a game studio with good licensing or not from a game studio. So we'll see. And then for anybody who wants to integrate hand tracking into some new headset, or if somebody wants us to try something, we want to do contract work for that. Those are like super very high level motivations and goals. So now I'm going to get into what we've actually done so far. So back about a year ago, I joined Collabora and some work had already been happening. And it was basically my job to take already trained models and actually deploy them. So this took like 4 months. I started in May and finished in October, and then I had a bunch of school, so not much happened. You can see, I'm just gonna very quickly skip through this because you can see this on our blog. The main thing I want to point out is, like, it looks nice, but you can see a lot of judder, and it also took me like 10 or 15 takes to get something without problems. But like today I'm gonna demo this live, and the hand tracking isn't gonna be what breaks. So I actually think nothing's gonna break, but we'll see. So yeah, yes, we'll see. So there were so many problems. I'm gonna skip over these. You can read the blog post. The cool stuff we learned is that Onyx is like open format for machine learning models. It lets you define their structure as well as the parameters it uses to feed forward. So we're using that everywhere. It works very well. It works with like basically every machine learning inference and training thing. And then Onyx runtime, it uses the same brand name, but all it is a piece of software that can run these models. Many other ones can do it now, but it's the one that has the brand name, so take that as you will. I found it to be very fast, and also very encouragingly, we can kind of do everything on CPU, and we don't need CUDA. And we don't need to mess with OpenCL, so that makes a lot of things really easy. So basically, we did that, and then in the beginning of 2022, we started on like the real version. So its code name is Mercury. If you hear me talking about Mercury hand tracking, that's the main thing I've been working on. Basically, it sees in grayscale. You can use it with RGB cameras, but it gets converted to grayscale first. This is very nice for a lot of VR headsets who don't have RGB cameras because they have lower light efficiency. And then as improvements from MediaPipe, I trained a hand detector that at the same time as detecting your hands, it also figures out which one is the left hand, which one is the right hand. And that solves many problems as opposed to just detecting any hands anywhere in the image, because generally it's good at not detecting other people's hands, and it's also good at looking at the direction your forearm is going to get context for which handedness it thinks this is. And then the key point estimator is similar. A big divergence from MediaPipe is that every image we feed into it, if it's a right hand, we flip it so that it doesn't have to learn as much, and it can like stay focused on estimating the hand pose of only one type of hand. And then, my mouse on? Yes, okay. And then all this is the nonlinear optimizer and also pose prediction to not waste time redetecting the hand if you already know where it is. So yeah, I'm doing this in a strange order. So this is just to show you, like, this is happening like over the course of a few months. So in March 2022, I had earlier versions of the models trained, but you can clearly see a lot of high frequency jitter. Like you can see the hand is going crazy, and I'm going to try to draw stuff in a second. And you can see it loses track of pinch, and the lines are not very smooth. And then in June, let's see, let's find a good part of it. I basically made a new technique for taking the 2D hand pose estimations and projecting them back into 3D, which had significantly less jitter and it was more accurate. So you can see I'm starting to be able to like actually draw stuff. I'm pretty sure I'm drawing a tree, yeah. So, and then actually, because I think this is going to work, I'm just going to demo what we have today. So, give me 1 second. Yep. Where is it? Is it gone? It is gone. I swear I launched it. Interesting. It's very gone. Yeah, the webcam is not connected. Let's see. There we go. Cool. All right. Perfect. So let's hope our slam didn't die. Yep, it's all good. Oh, it drifted a bunch. Going to briefly restart this. All right. Perfect. So you can see this is oh my god. Okay. So yes, I said I wasn't going to do that. So you can see this is a much more boring demo. It's like it's got more stuff, but it's got less pieces to it. So you can see this works pretty well. I can grab stuff, I can move it. Yep. It's good for like actually it's good for like living in VR. You can see this is my avatar, and I just have it mirrored. So it's displaying my avatar over me as well as in a mirror. So you can see I can interact with myself, and this works. And then if I can find the menu, there it is. We can also draw. This works pretty well. So you can see. Oh, I let's go back. So you can see it didn't misdetect my pinch gesture anywhere. Like it generally just gets this correct now, which is really good to see. You can see it's robust to actually do this. You can see it's robust to occlusion. Like I can cover up all of my fingers and it still knows that my hand joints must be around there. it breaks a little bit. There's a lot of hand poses it doesn't like. You can find them if you play with it for a while. But in general, this is or is very close to usable for what we actually want it for. So let's see. Oh yeah. You can see some other fun stuff. I started this in the wrong. There it is. Yes, cool. So this is a lot like Nova's thing. Like you can see, I can spawn models. I can grab them. I can look at them. Can spawn a tiny clone of me. Oh, let's see. Here it is. So look, it's really tiny. Okay, that's there's a few more things I can show off, but the basic thing I want to say is this is mostly usable for interactions. There are some edge cases, and I think it's been detecting my hands in places where they shouldn't be and messing with the UI. I'm pretty sure I've seen that a few times now, but that's pretty much that. Let me exit out of Monado and stuff. So I kind of chose to put the demo in the middle because, like, I figured the way I like to explain everything to people is like backwards. Like I want like math textbooks, they always love to show you like the definitions first and go through all of the theory and not just show you what the point of it is. So I figured I would just like show you what it's actually doing. Can skip that. Okay. So the rest of this talk is going to be getting into the weeds of how our hand tracking actually works. They're fun weeds. So this is a very crazy flowchart I made of how this works. I'm going to come back to this. This is not explainable in one shot, but it's getting pretty big these days. So again, the new hand detector, it sees in grayscale. The images are 320 by 240. We're using a model architecture off the shelf called SimDR. And this one isn't very fast. It just was the first one that worked. So I'm still pretty happy with it. So the main data sets we used were Epic Kitchens. This one is the most important one because it's about 100 hours of video of people doing stuff in their kitchen, and it happens to have bounding box annotations for left and right hands, which means that we can use it. And then also Ego hands and TV hand and Coco hand, which are a lot smaller. And then also a relatively small data set we collected on a different variant of this. All right, the camera's here, I forgot. So basically, that's that. There's a lot of work that goes into getting these data sets from the web, evaluating like, does this even have the annotations I want? And then writing a bunch of code in PyTorch to stick them all together and make sure there's no mistakes in them. You can see here, this is, I just don't remember. Okay, so this is the annotator that we made to have some extra data for our hand detector. So the main thing that's cool about this is that we're using a already existing hand detector to make most of the detections, and this is just like me fixing where it went wrong. Most of the time, I just went through and said, yep, all these are correct. So augmented annotation is going to be more and more relevant, I think. because you can train a neural net that gets it right most of the time, and you can write software that just skips you to, why did it unmaximize? Okay, and you can write software that just takes you to fixing the incorrect annotations, which is a very big time saver. So that's what annotation looks like. And then when we're training, detecting your hands.
There's a question from audience saying what's a detector used for?
It's for detecting your hands so that when the cameras see your hands, it'll know where your hands are. So while we're training, we're doing really basic data augmentations. We're just applying a random rotation to the image, and I think also a random scaling, so that we can take like our 100,000 images and every training run make each one look a little bit different each time. So you can see like these are the ground truth bounding boxes, and it's learning to predict these. And then you can see here, this is a very simplified view of what it looked like as I was debugging it. So you can see, look, it knows like it knows yellow is the left hand and red is the right hand. So it even works with crossed over hands, which isn't surprising. And then okay, there we are. And then the actual outputs is all using heat maps. So you can see this is my left hand, and you can see a corresponding bright spot in the image for my left hand, and same for my right hand. And these ones are really interesting because these are predicting the hand's size. So basically, we get the hand size from the center of the bright spot here. So you can see that this is dark because it's small, and this one is bright because it's big. But the really cool thing is that since we're using heat maps, as it's training, it can smoothly adjust its guesses about the hand's position and size without having any place where it gets stuck while it's doing gradient descent. So heat maps are very important for motion tracking when you don't have all the information, because you need everything to be predicting Gaussian distributions, or else you're not going to know what you know and what you don't know. So then the key point estimator is very similar, except for instead of looking for your hands, it's for when you already know where your hands are, and we're just estimating where each joint on the hand is. So most key point estimators predict 21 locations, one for your wrist, and then for each joint on your thumb and fingers. And it skips the metacarpals because those are hard to annotate. So this one also is very small. It sees in grayscale and 128 by 128. I want to look back at this and see if there are better input formats that perform better with the same or lower compute. So this is using almost the same model architecture as the hand tracking on Oculus Quest. And that's just coming from the paper that they published. So this isn't any reverse engineering. They said this is what we were doing, and we replicated it, and yep, it works. So and again, the data sets are a very small data set I collected in front of a green screen, and we just annotated it using MediaPipe. And then we are using the CMU Panoptic data set and Freihand. Both of those are pretty good, but I think they both only have 2D landmarks. Like they only have the key point position in 2D with the image. And then also we have an artificial data set. So let's see. So you can see this is similar to what you were seeing in the other slide. This is the input image that actually gets fed into the key point estimator. And then each of these heat maps are predicting the the 2D probability distribution of where we think that hand key point must be. So you can see this is the wrist, corresponds to there, and then this, for example, is the index finger tip, which also is in the right place. And then we do similar stuff predicting each key point's depth relative to the middle proximal joint. So you can see this is the middle proximal joint. It's exactly in the center. And then you can see it's trying to predict the depths for all of the other joints. You can see there's a lot of ambiguity here. So for example, right here it predicted 2 different places, and it's up to the C++ code I wrote to interpret this as it doesn't know, and we shouldn't take this one into account, which we do. So then, like, this is honestly the big problem I think we're solving. A bunch of public data sets for training key point estimators, most of them have problems. Like, a lot of them have random images that aren't related to each other. Like, there's no smooth sequences of camera frames. It's all just somebody snapped a picture and then moved somewhere else and snapped another picture. So this means if you want to train like recurrent architectures that have some memory of what has happened, it's very hard to use these data sets for it. And for anybody collecting a new data set, that's the main thing you have to do. You have to use video. And then similarly, most data sets don't come with camera calibrations, and they only annotate the landmarks in 2D image space, which means that if you want to predict depth data for the hand joints, you're going to have a lot of trouble. And then again, Interhand does this right, but the most consistent thing that they all do wrong is that they have some percentage of incorrect annotations that are really hard to get rid of. And Interhand was surprisingly bad here. I'm not sure what was going on. I hope they fixed it, but I'm not sure. And then you have a bunch of issues with privacy. You don't want people's fingerprints in here. You might not want to collect in people's houses. And then licensing. Everything has a non-commercial license. So you can do research with them, but you can't make stuff with them. So collecting a real data set is risky. You have to worry about if your cameras are going to work during the day, if your hard drives are going to work, however your annotation pipeline works. Is that going to cost a lot of money? Are you using the right kind of cameras? Like, you could use normal cameras, but you could use depth cameras. You could use event cameras. And if this is going to take you a few months, like, maybe something really new is going to come out and you want to switch to that. And also, cameras are expensive. Big studios like big mocap studios basically are expensive. So this is all stuff that made me wonder, like, is there like a sneaky way around this? And the answer is yes. So all of these images are not real people's hands. They mostly look real, but none of them are real. These are generated from really high quality 3D scans of people's hands, and then we basically import them into Blender and repose them in different ways. And we've found that this does work even by itself. So this was a couple weeks ago. You can see this key point estimator was trained on exclusively artificial data, and you can see I'm testing that gesture because that one has been having problems. It's been having data problems where they're not represented in public data sets for some reason. So but it's very important. You have everybody's going to try that. You have to make sure it works. So this works well for the most part. And you can see it's like, so it's very robust to your hand being at the very edge of the image. It understands what the edge of an image is and that the rest of your hand is there. So this, trying to fix it. There we go. Oh, it's okay. When I full screen the video, it gets mad. Okay. So let's see. Basically, I looked into I looked into generating like totally fake meshes of people's hands, like not even from scans, just like, can we make a feed-forward neural net that just does it, like a GAN or something? And as far as I can tell, no. So we're using more classical techniques. Those were collected using photogrammetry, and we just bought them from an asset store, and obviously the asset store wants to keep selling them, so we can't just redistribute them. So we are going to figure this out. It's not going to be a problem. So, and then I took these meshes and rigged them in Blender, and then I wrote basically a very crazy pipeline to create a whole bunch of mocap data that's also mostly fake, so that we can move the fake hands around using this fake data. And then we're running Blender to set up this animation and render it as cube maps, and then redistort the image. Actually, let me show you that. You can see this one shows it well. Like VR headset cameras have distortion, and if you don't represent that in the data, your model is going to get really confused. So our pipeline can basically take these not distorted images from Blender and use real camera calibrations to make it look exactly like it had come out of a headset. Okay, let's see. And then we can trivially get the annotations because we have the pose data. We use it to make the image, so we just write the pose data back. And then that code is published. It works. But we just need to make sure there are hand scans that people can actually use. So and this is just talking about training the keyboard estimator. It's, again, a lot of shared code with the hand detector. You're just getting a bunch of PyTorch data sets and sticking them all together. There's this one library I'm using all the time now, which I want to shout out. It's called Nunchucks. Basically, if your data set has problems and you didn't catch them until you're already training, you can write code that catches these problems and when the data loader code gets called, it can say, oh wait, this one isn't okay, and it'll just use the next one in the sequence. That one saved me a few times. And then I had to write some kind of fancy loss functions because some data sets don't have depth data and some do. And then again, the training code is published, and that one is ready to use. So, and then the last big component is not machine learning. You have 2D predictions of your hand pose, and you're like, okay, I know where this is in camera space, but the user doesn't care about that at all. They only care about having it overlay data over their real hand and know where their real hand is relative to their head in 3D space. So doing this is surprisingly tricky. You can kind of think like, if we have two cameras, like maybe you can look at one key point and like estimate like a triangle between the two cameras and the key point and like use trigonometry to figure out the depth. And that's actually what I did. But it just was very not robust because like, again, no Gaussian priors. If your machine learning model gives you a wrong prediction, you have to use it, and it'll result in a very wrong 3D key point prediction. So another way to do this is you can try to use these crappy projected 3D points and use something like inverse kinematics to like wiggle the 3D hand pose to the right place. But all of these techniques are really tricky, and it's really hard to make something that's mathematically optimal. So instead of trying to make procedures to make your hand pose be right, instead you can basically just use the same techniques behind machine learning in real time, where you just write a function that describes how good a 3D pose estimate is given the 2D predictions. So it's basically just like you take a really low dimensional vector encoding the hand's pose in 3D. You evaluate this to joint poses relative to the camera, and then you compare those to the 2D predictions from the key point estimators, and if they're really close to the 2D predictions, then you have a good solution. If they're really far away, you have a bad solution. And it's kind of great, because it's like you can kind of just pontificate to your computer what counts as a good solution, and using gradient descent or Levenberg-Marquardt, it will just find a solution very quickly. And if you can provide Jacobians that basically describe like what direction it has to bump the hand pose in to get a better estimate, it's very fast. It converges. I think it converges in like unoptimized code like 0.5 milliseconds and maybe like 50 iterations. So Levenberg-Marquardt is a big thing for estimating kind of unknown systems. It's very popular. The main competitor is just Kalman filtering, but like we think that Levenberg-Marquardt is getting used for lighthouse tracking, constellation tracking, and SLAM. It is getting used for RSLAM. So this is very good, very flexible. It seems to work, and it also just anneals through a lot of problems. So, okay. So these are just a few demos showing. That one is not going to be good because I realize our resolution is kind of low. So let me try. This one's fun. So basically, we have two unaligned point clouds, and this is going to align them in like 6 iterations. And it's only aligning them on the basis of how close is each corresponding point to the target point. It doesn't know anything else about this system. Like that's all it knows. And then you can see that this is like, is that gonna load? Yes. I think my Wi-Fi here is kind of spotty because it's not loading in a high resolution. Okay, perfect. So this is development footage of basically I have some kind of fudged 2D predictions from a key point estimator, and you can see our Levenberg-Marquardt implementation trying its best to keep up with them. You can see it breaks around here because the predictions were very wrong here. So that's very cool stuff. I basically stumbled across this, but this is like seems to be a very good general technique for like solving state estimation and robotics problems. So very cool stuff. And I need to come on. Wants to play the videos. There we go. So that's pretty much everything about how our hand tracking works now. And then this is just like a quick overview of what we're going to do next. Basically just right after this conference. So the artificial data set worked shockingly well, but it has a lot of problems in terms of data diversity. Like, it has very good skin tone diversity, which I'm happy about, but it doesn't include like clothing, it doesn't include watches, rings, or tattoos. So if you try it now, you have to roll up your sleeves, for example. And then it can tend to generate really scary looking poses. And then a crazy thing I want to try is instead of, we're just using linear blend skinning to repose the model. So I've been thinking about like simple ways to simulate like the way your skin kind of folds over itself better than just like lerping between two transformation matrices. So then we just need more mocap data, and then I really want to do like intertwining fingers, like really tough hand poses, and like see what's the trickiest artificial data we can actually generate. And then also at some point we should try simulating other types of cameras. So that's the main like actual improvements to the data set we want to make. And then another big one for us is we've trained a pretty good hand pose estimation pipeline, and it's not clear how much better it can get. So I really want to try training some really accurate neural nets that don't run in real time and see how good their guesses can get. One really interesting thing I want to try is recently we've seen a lot of progress with DALL-E 2 and Stable Diffusion, where they start with random noise and an input string, and basically every iteration they try to denoise the noise, and then it adds a bit more noise back, and then it denoises again. And over time, it converges on something that also should match the input string you gave it. So for us, what that would look more like is you start with a very noisy prediction of the hand pose, ideally using really noisy heat maps or something, and then every iteration, it denoises the heat maps and using the input image as a reference to figure out how to fix stuff. I don't believe I've seen that tried before, so that one will be really interesting. And then there's basically a bunch of really small stuff, like our nonlinear optimizer fails sometimes. I think I know why. We need to make it better at knowing when it doesn't know the hand pose. And then there's a bunch of other stuff to try. There's a lot of machine learning is just try stuff, and then some of it works. And then we want to do elbow tracking and like good tracking from webcams, and then like we want to publish like everything, because we want everybody, like, it's the biggest thing that's bugged me is how hard it is to take prior research and actually apply it. So that's kind of my crusade to make something good people can use. So yep, I think that's the end. Again, we just got to plug, we are hiring. If any of this is interesting to you, if you have cool ideas, come talk to us. The worst thing we're going to say is maybe. And yep, I think that's it.
Thank you so much, Moses. We can maybe have like one tiny question for the audience, okay? So I'm just gonna mix two questions that were kind of alike.
Okay.
Going back a bit, the middle of your talk, people were wondering about the use of markers. So it might not make sense towards the end of your presentation, but how are markers could be used, and also how about wearables like gloves? Would they block ordinary hand tracking algorithms? So I'd like to maybe take a few minutes to wrap up on this question.
Okay.
And that'll be all time we have. Thanks.
Okay. So very small gloves, like medical gloves, will work fine as is. Our hand tracking doesn't care. But stuff like the Lucid VR open gloves, that will absolutely interfere. And I honestly don't see a good reason to mix those two anyway. Like, if you have really big haptic gloves, I hope they're tracking your hand pose really well. You don't need cameras anymore. And then markers, yes, it's very possible to mount small markers on your fingers. And I encourage you to try it. It should work, but we want to do markerless, so it's not really an interest of mine. And then the last thing, which I think somebody might have been getting at, is wearables. And maybe could you put a marker down here? Like, could you put a bracelet or like a wristband on that improves the tracking? And the answer is yes. What has been tried and also needs open research done around it is basically a wristband that has an accelerometer in it, and also sensors that can sense your muscle impulses. And what we can do with those is you can train a neural net on your muscle impulses and make a pretty good guess about the finger pose. And you can use an IMU to fix up your guesses when the hand is moving really quickly or if it's occluded. But obviously you won't know if you have a wristband, you won't know the wristband's pose relative to like where it is on your arm. So the best, like a really good thing to try is basically fusing the two in the Levenberg Marquardt block of code. Literally just add terms that say, hey, your 3D pose should match up with what the IMU is saying or with what the myoelectric sensors are saying. So that is something that absolutely should be tried, yes.
Thank you so much, Moses. So nice talk and amazing work. Thanks again.
So this talk is about ILLIXR, which stands for Illinois Extended Reality, Testbed, and Consortium. And I'm Sarita Adve. I'm a professor at University of Illinois. We have a few people from the and Bill, and there are several others who should have given this talk but couldn't make it. Okay, so this is going to be a little bit different because I think we are the only academics here, if I understand correctly. Maybe a slightly different perspective. Okay, so I do research in computer architecture and systems, so hardware, software systems, etc. And a few years ago, my senior grad student, Huzaifa Muhammad, and I, we were, So I was going to say this is going to be a little bit different in terms of background, but all of those difficulties know what I meant. But yeah, okay, so this is about ILLIXR. So a few years ago, Zephyr, my student and I, we got very intrigued by the transformative potential of extended reality. And we said, okay, we want to do our research, build systems for extended reality. And this was actually a sort of a dream for a researcher, because there is an orders of magnitude gap between the systems we have today and what we desire in terms of not just performance, but power and the quality of experience. Right, so if you take power, you think about wearing glasses that are this form factor, walking around all day long. The power envelope that you want to stay within, the compute power envelope, is about 200 milliwatts. And today's state-of-the-art AR glasses, well, we have 7 watts, right? So orders of magnitude difference. Same thing with weight, same thing with resolution, and so on. So we did a whole survey of what's out there, what's really desirable, and it's all in a paper that we wrote, and it all seemed really exciting. Okay, orders of magnitude gap, great potential for research here. But then there were also many challenges. So it's not just that we have to overcome this orders of magnitude gap with Moore's law closing and so on, but also that this area requires diverse expertise in various research topics like graphics, vision, audio, video, etc. Complex metrics, the goodness metrics of XR systems are not well defined. And it was clear that it's not, the hardware people are not going to solve this problem. We really need a full system approach to deal with these systems. But then the most difficult challenge of all, we kept running into the fact that everything out there was closed behind company firewalls. There were very few participants, and it was really hard to do research. We didn't even know what to build, what the requirements were, and so on. And so that is what motivated us. There was a large barrier to entry for open R&D in this space, and so that's how we decided, okay, we want to first democratize XR systems research, development, and benchmarking, and we really care about benchmarking, because unless you can, we strongly believe if you can't measure something, there's no way to build it, to improve it by building something new. So that's what led to the ILLIXR project. And today, ILLIXR is an open source full system XR testbed. The goal is to have state-of-the-art XR components with a modular runtime. It is OpenXR compatible thanks to the Monado folks here. And we've used it to extensively characterize the performance and power requirements and power usage and the quality you get for XR systems. And it's being used for a large number of research projects covering all the way from hardware all the way up to software. So before I go into a deep dive of what ILLIXR is, I just want to show you some demos. Well, there are videos. I don't have real life things here. We didn't bring stuff along. Just to show that this stuff is real. So this is just sort of day to day how we use ILLIXR. My student Josefa is walking around in our lab here in this grayscale image with cameras and IMU. This is a third-party view of the virtual space that he is traversing with the headset here. These are the iBuffers that ILLIXR is producing. We have a debug window, etc. And then for doing more headset-based experiments, we have, this is with the Northstar headset, thanks to Bryan and company. So we have this nice portable machine that my student is wheeling around so that his friend can have a nice experience traversing the Sponza castle here. And ILLIXR is running on the PC that Jeffrey is rolling around. And we're using the Northstar just as a display to send pixels to the Northstar. Tracking is happening inside ILLIXR, rendering, etc. All of that is happening on the PC in our system. And you can see that tracking works pretty well, and so on. Okay, and then if Joseph decided one day he didn't want Jeffrey going around with him, then he can wear this backpack PC, and ILLIXR is running on that, and he can walk around and have his experience. So more recently, we realized that 200 milliwatts is a pretty steep power constraint, and so it's likely not going to be possible, even after applying all sorts of hardware smarts. It's probably not going to be possible to do everything we want to do on the headset, right? And even otherwise, you want to have multi-user experiences, so not everything is going to be happening on your headset. And so we started to offload components of ILLIXR to a server. And so this is just a demo showing you offloading of VIO, of head tracking. So this is the backpack PC on which ILLIXR is running. This is a display just to show you what ILLIXR is putting out. Here is a server that's running VIO. Everything else is running on the backpack PC. And that's the monitor for the server. And you can see again that tracking is working pretty well in this scenario. So here the server is right next to the backpack, but we've actually offloaded our VIO, our head tracking, onto AWS, for example, so Amazon's cloud, and it works reasonably well. So we are doing a lot of experiments with Wi-Fi, with 5G, using compression, etc., and writing a paper that talks about the trade-offs and so on. But so far, experience is pretty good. In about 2 weeks, we will have more detailed numbers and measurements to show what's going on. Okay, so all that is. I shouldn't go this way, right? Okay, so all that is great, right? So we did a lot of work, got things running, but of course we know that we cannot do achieve our dream of democratizing XR R&D and benchmarking by ourselves, and so. We started the ILLIXR Consortium, encouraged by several supporters, both from industry and academia. So ARM, Meta, Micron, etc., are part of our consortium. And the stated goals for the consortium are we want to create, building off ILLIXR, create a reference open source testbed that serves as a reference for researchers and developers and companies who want to do benchmarking. And so this reference should have state-of-the-art components and very well-defined interfaces. So third parties who want to build new trackers, sell new trackers to another company can easily plug and play, switch implementations, and show how the head tracker performs in the context of an end-to-end system. Right, so we want this to be modular and extensible, and lots of telemetry, lots of measurements, so that we can show performance, power, etc. And then create a benchmarking methodology. So today there's no real methodology by which we can say system A is better than system B. Right, there's no standardization. Standard is a faraway term. There's no agreement. There's no consensus, even community-wide, as far as what applications to run, what should the data sets be, what system configurations to run at, what kind of metrics to use even, right? You compare head tracking, what kind of metrics do you use? So we want to also solve that problem through this consortium, bring the community together to help solve this problem. And then finally, build the XR systems research and development community. And it's great, Northstar, Monado have these wonderful, wonderful communities. We've benefited from these. The research community is not quite, there isn't such a strong sort of XR community per se, and we'd like to bring all of that together. So that's what the consortium is trying to achieve. And, we have bi-weekly meetings, and people from here have come and given talks at our meetings, and Moses, thank you, is going to come and give a talk next week on the hand tracking work. So I invite all of you here to also participate. Just get in touch with us. We have a Discord, and help us achieve this dream together. Right? So this is our team. Just want to make sure that I acknowledge everybody, and in particular Josefa, who really should have been giving this talk, but he couldn't make it at the last minute. He has been leading the entire project, but with lots and lots of contributions, with lots of students. Of course, this would not happen without a large team. And then I also want to thank our primary funding sponsors and give you a sense of where we get funded from. So a lot of the initial work happened with, there was a research center called ADA that's funded by DARPA and SRC being the Semiconductor Research Corporation. DARPA funded us for hardware software co-design methodologies for an adjacent domain, in particular autonomous vehicles. And then NSF put in last year $1 million for making ILLIXR be a community, a computer science community-wide infrastructure that all computer scientists could use for research. And then just recently, this project is starting actually this month. NSF has now funded for us, it's a nearly $5 million funding for doing research in distributed XR. And then I'm very excited that my University of Illinois, is investing, so this is like hot off the press almost, investing $4 million for us to create a center for immersive computing on campus that will bring together people who are creating the immersive technologies, people who are using immersive technologies for education. We want to build a distributed XR infrastructure that is public, and researchers and developers can use it to further research and further this area. So we have many. It's a very ambitious kind of thinking, but we started with 2 people. We've gathered a lot of people along the way who are going to participate in all of this, and hopefully, we can all keep working together. Okay, and then we're also, the obligatory plug, right? So hiring programmers, and if there are students here who want to do whatever degrees, postdocs, research staff, project management staff, etc. So lots of positions open. So now let me give you a sense of what, deeper dive into ILLIXR. So here is a basic overview. So just like any XR system, ILLIXR has a perception subsystem, a visual subsystem, and an audio subsystem. And all of these 3 communicate with each other through the ILLIXR communication interface and runtime. And on top, we run XR applications, and we can run these an XR application write it directly to ILLIXR. If we want to use OpenXR, then we use Monado as the OpenXR interface. And then all of this runs on, you saw the PC, but we can also run on NVIDIA Jetsons, and we've run on ARM boards, and the hardware that we run on is expanding. And then, as I said recently, we are starting to work on offloading several of these components. So we have already built in the offload for VIO, but then there's other things that, for example, rendering that we also plan to do. So just to give you an idea of what all we have in these subsystems. So for perception, as you all know, perception is all about figuring out where in the world the user is and what the world looks like around them. So we have sensors, cameras, and IMUs. We do visual inertial odometry, all sorts of odometry and SLAM. Really, it's not just restricted to visual inertial. This provides the position and the head orientation of the pose, but does this at a slower rate. For a faster rate, we can use the IMU. We have an IMU integrator that provides a higher frequency pose estimate, and then a pose predictor that extrapolates the pose for a future timestamp that can be used for warping, etc. We also have scene reconstruction, so using depth cameras to build a dense 3D map of the world. And then for eye tracking, we don't have the hardware we don't have eye tracking cameras, so we're still using data sets, but we have an eye tracking model that works pretty well. Okay, for the visual pipeline, we do time warp or asynchronous reprojection. We do have space warp code, but it's not fully integrated yet. I won't go into description for why warping is necessary. I think this group knows that. We do lens distortion, chromatic aberration correction, and then we don't have holographic displays, obviously, but we do have code that we run to help us benchmark what it will take to have computational holography. And then for audio, we do 3D spatial audio encoding and playback, including binauralization. And yeah, so these are the components that we have in ILLIXR. But of course, XR is not just these individual components. XR is all about putting the system together. And there's lots going on in the system, right? And so we need to build that runtime that puts this together. So for example, you have the IMU running at a very high frequency. You have the camera running at a lower frequency than that. You have the VIO taking input from the IMU and the camera, and then the IMU integrator taking input from the VIO and the IMU. There's eye tracking, there's scene reconstruction, and the application is getting all of this information. Reprojection connects with the application and the IMU integrator, et cetera, et cetera. Right. And so there's a lot of components going on here at different frequencies, multiple interacting pipelines, and there's all sorts of different dependencies. So the solid arrows here show what we call synchronous dependencies, meaning that the consumer will not move forward unless it gets the latest output from the producer. Whereas the dotted line, the dashed lines here are asynchronous dependencies, meaning that the consumer is happy with whatever information is available, even if it's not the latest thing. And so ILLIXR puts all of this together. So our runtime, which we call switchboard, is modular and very flexible, and handles all of these dependencies and the scheduling of all of these components. We have been very, very careful, and this is actually a big deal for us, since we want this to be a research test bed, that these components it'd be very easy to swap components in and out of ILLIXR. So we have multiple implementations of VIO, multiple implementations of scene reconstruction, and we have uniform interfaces for them, and it's relatively easy. I mean, it's not like super easy because you have to understand what the algorithms are doing and make them have those interfaces. But once you have that, then it's easy to swap things in and out. And so each of these components is separately compiled, independently compiled, and dynamically linked. And yeah, so we put in a lot of emphasis on this type of modularity and flexibility. But at the same time, we also want efficiency. And so we spend a lot of time on efficiency as well. Each component essentially specifies event streams to publish and subscribe, so it's a uniform interface. And we can have synchronous or asynchronous consumers, and all of the communication happens copy-free through shared memory so that we have efficiency. So the end-to-end system can balance flexibility with efficiency. Okay, so what about applications? As I said, we can write, toyish applications directly to ILLIXR, but of course the power really these days is in running OpenXR applications, and we were, this was I think when Monado was getting started and OpenXR was getting started, and we were really delighted to see this happen. I don't know what we were thinking, how we would have got applications to run on ILLIXR if this effort hadn't happened, right? So we use Monado as an OpenXR interface, and what I'll show you next is with the Godot game engine numbers and using Godot, but now we also run Unreal. And then we collect a lot of quality metrics like motion to photon latency. We collect image quality metrics like SSIM and FLIP, mesh quality metrics. And we have extensive telemetry, so frame rates, missed frames, time distributions, power, and so on. Because again, the goal is to improve the system, and we cannot improve unless we measure is a huge philosophy. So here's a list of all the ILLIXR components today. Actually, this is out of date. We have many more now, but the key point here is there's multiple different VIOs, multiple scene reconstruction algorithms, etc., and we can swap them in and out relatively easily. Okay, so using all of this, well, what did we find? Again, this is not a research conference, so I'm not going to spend too much time, but I just want to give you a sense of the power of ILLIXR. First of all, the platforms that we run on, again, I said, high-end desktop machine as well as embedded machines like the NVIDIA Jetson. And the numbers I'm going to show you next are with applications like running on Godot, like Sponza, Materials, Platformer, if you're familiar with all of this. And so the things we've done an extensive analysis. It's all documented in the paper. For a particular configuration with ILLIXR, we've talked about, seeing the frame rate, where are frames dropping, what's really the bottleneck, how long each of these frames are taking in different components, like how long does VIO take, how long does the application take, etc. The distribution, right? So this is a timeline for the execution, and we can figure out when things are going bad, what is the variability, why are things interfering with each other. We can figure out the distribution, meaning, what is the fraction of time, what is the fraction of cycles that the CPU or the GPU is spending on a particular component. We can do similar things for power. Is the power going in the CPU, in the GPU, in the display, or the rest of the SoC infrastructure? We can figure out, as I said, motion to photon latency, image quality, and we can do this on timelines. So there's a lot of information here, and we have evaluated all of this, spent a lot of time looking at all this information. And I think these are the first published performance, power, and QoE results for an end-to-end XR system that are out there in the open. I mean, we'd love to see other results and compare and contrast. And then these gave us many, many implications in terms of research for how do we build hardware? How do we build systems? What should we really be focusing on? So again, I'm not going to go through all of this in detail. I'm happy to talk about any of this later, and it's all in our paper. But ILLIXR essentially provides a very rich playground for systems research and has opened up, or at least motivated, a lot of work that we and many people are doing. But more than anything, to me, XR really motivates a new style of research and work in general, which is about co-designing across the system stack. So not just the algorithms, but also the system runtimes, the languages and the compilers, the hardware architecture, and even semiconductor technologies. Like, for example, in-sensor compute changes how these systems will be built. And so we are very interested in bringing these communities together and enabling all of this research, and of course, performing a lot of this ourselves. And then it's not just the headset, but moving forward, as I said, the real power of XR is in multi-user experiences. And so again, it's not just co-designing in the layers of the headset, but bringing the headset together with multiple headsets, servers on premise, on the edge, in the cloud. How do you co-design all this? How do you build these systems in a way that provides the experiences we want? Right? So this is really a new style of research. And then the other aspect of this is it's end-to-end quality driven. So unlike a lot of systems research tends to be, oh, I reduced the power by this much and I'm happy. But no, it's not just about reducing the power, it's about also, ensuring that the user does not barf, right? So, how do we do that type of research? And there's a whole bunch of research being done. So we are working with collaborators on 3D integration of sensing and compute and memory. That changes how we think about many of these algorithms, looking at how to represent all of this heterogeneous parallelism in software, various cross-component co-design techniques, looking at multiple accelerators, offloading computation, as I said, things like eye-tracked foveation, how does that interact with everything else, and security and privacy. And more recently, working with our medical school, they are at the forefront of using XR for healthcare. And so that's an awesome use case for us. So we are wanting to deploy some of that, the advances that they have there into our system and conversely help guide our research. So that was on the research side. As far as the ILLIXR testbed itself is concerned, we have work going all the time. So in particular, some of the immediate things, some things that are ongoing that we have are new components. So we wanted to see an understanding. So we've spent a lot of time on reconstruction. We haven't started scene understanding yet, but that's something something we want to do soon. We are hoping that with Moses's talk in our consortium next week, we can have so we have efforts on hand tracking using various options, including Monados, and hopefully Moses will get us up and running on that one. So thank you for that again. We have eye-tracked foveated rendering. We're working with NVIDIA on this, spatial reprojection, neural rendering techniques, etc. I already talked about offloading. That's a big, distributed XR is a big topic for us now, including rendering. And how do you do split rendering and computation offloading architecturally? How do you make those decisions, right? How do you build your system so that you make good decisions about, okay, when do I have enough bandwidth to offload? Is compression going to take up too much energy? Is this the right thing to offload? When do I do it? So this is not just about offloading one component. It's about building an entire architecture so that these decisions can be made in a reasonable way. And then multi-user XR, my colleague Anthony Rowe at CMU has built Arena, which is a multi-user XR system that we want to put on top of ILLIXR. And so that effort is ongoing. We want to broaden our hardware and software platforms. Our Android port is underway, and lots of progress made. We should be able to announce this soon. We want to create and curate data sets and applications, and also add hardware in the loop. So pre-silicon hardware, if you have FPGAs or simulations, how do we actually put that in the context of this entire system and still get reasonable results? So we're working on that as well. And then incorporate all of the research results. So yeah, again, we are looking for talented people. So if you're interested in working in an academic position, the pay is not as high as commercial positions, but we have other advantages, and we love to work as a community. So reach out to us. Yeah, to conclude, ILLIXR is a rich playground, we think, and help us move the consortium work forward together. Yeah, that's all I have to say.
Thank you very much. Thank you, Sarita. We have time for some questions, and we already have one from our remote viewers here. So there is actually multiple questions. It's about the ongoing work for offloading in particular. So is offloading currently done on a local network? And is it possible to add more offloading devices to ILLIXR, like in a distributed computing scenario?
Yeah. So right now, our offloading, that's exactly the research we are doing, is what type of networks make sense. So Wi-Fi doesn't seem to be a problem at all. I can say honestly that works. So we are offloading. When I talk about our experiments, this is actually to AWS, right? So this is to the cloud, far away, right? And then locally, what networks do we use? We use Wi-Fi. 5G is tricky. We definitely need compression for 5G. And we think it's working, but I don't want, we haven't done enough experimentation. I don't want to say for sure, right? In about 15 days, we'll have this paper written, and then I'll be able to give you a definitive answer. So for the sort of scenarios we've tried, it seems to work, but we're trying to push it. And of course, if you have more users and you're constraining bandwidth and there's contention and so on, things will be affected. But we haven't done the full range of experiments.
And the sub-question was, can we already find workable code for offloading in current GitHub, or?
Yeah, we've actually released it. Yeah,
all right.
just for VIO. So this is so the GitHub code that you will find is sort of tied to VIO, but we have an internal version that we are using that we've shared with others. So Intel, for example, is working with us on this, and we are very happy to. I mean, if we get questions, we will release it. Yeah. But there is a basic offload code out there. Yeah.
Any questions from the audience? So we have one question here from the audience.
Yeah, is ILLIXR something that like an application developer would ever use directly, or are you more like benchmarking and making recommendations for architecture?
Yeah, so think about ILLIXR as right now the way it is as the headset, right? And then so if you're writing OpenXR compliant stuff, you're writing on top of Monado on top of ILLIXR, right? And well, on top of Unity or Unreal on top of Monado on top of ILLIXR, right? But going forward, right? There's so many constraints in this system. So having this really opaque kind of boundaries, right, between the game engines and the underlying tracking and the resource management that I talked about, right? Offloading. Today, if you want to offload rendering, those decisions happen inside Unity, for example, right? But that's not, I don't think that's the right place to make the decision, right? So what we are trying to do is re-architect the system so that we can bring in parts of rendering into the runtime, into ILLIXR, so that the system can make these decisions cooperatively, right, in a more reasonable way. Does that make sense?
You want to add some sub-question here?
So it's more than just benchmarking, like is something that I would ship with my application?
No, it's like having you wouldn't ship a valve index with your application, right?
Okay.
So this is a head. So we use Northstar's display or the valve index's display, right? Display from whatever headset, and we're running ILLIXR on hardware, right? That is essentially sending the pixels to the display, right? And then on top of our hardware, you can be running your machine, your application. Does that make sense? Okay. And then moving forward, we are planning on building our own SoCs, so own chips to get the hardware be better. Right now, we run ILLIXR on just off-the-shelf hardware like Jetsons and ARM boards, et cetera, right? But as we move forward, so we have an accelerator design for reconstruction, for example, and then we need to, well, there's still a ways to go, right? Prototype on an FPGA, tape it out, integrate it in the rest of the system, blah, blah. This is a fairly long-term project overall. Does that answer your question?
All right. Anyone else from the audience? We have a question. So Sarita, I will invite you to go back to your square feet.
Hello, Sarita. Nice talk. I wanted to ask if ILLIXR supports or is planning to support at some point emulating device constraints like restrictions of performance capabilities of a hardware device by emulating them like in a closed server or something like that to emulate performance of different parts of the system.
Sorry, I'm not sure I understood the question. So the question is ILLIXR planning to incorporate the performance or energy, for example, constraints of the device or bandwidth?
Right? Yeah, like being able to simulate constraints of a real device, but in a bigger device that can simulate multiple devices at the same time.
Yeah. So that's part of the game plan, right? That's a big part of the research is how do you do resource management and scheduling. We have taken one step. So we have a paper on arXiv right now that looks at scheduling just the CPU, okay? So that we are more effectively using it. So that system has VIO, it has time warp, it has IMU, and I don't remember what else, okay? And so if using our techniques, right, we use some solvers, etc., to figure out when is the right time, how much CPU to give to these different components. So that's like the first step towards what you're saying. But that $5 million grant that I talked about, a big part of that is going to go to this stuff. Yeah.
All right. Any more questions? I'm looking online. Sarita, I think that's it.
Okay,
so
great.
Thank you again very much for this very nice talk. And see you. Thanks.
Okay, hello, my name is Lucas. I am currently a sophomore at MIT studying electrical engineering and computer science. And VR haptic gloves have pretty much completely taken over my life. This right here is a picture of a old VR haptic glove that I built about a couple years ago. For anyone who doesn't understand the meme, basically the idea here is I've always wanted like real VR haptic gloves, and the best solution I've had is whatever I could put together at home. So I want to talk about the current state of the VR industry, the current state of virtual reality as a technology, and it's progressed very quickly. It's existed for a while, but we've gone from an age of completely experimental technologies and things that require a lot of tinkering to something much closer to a polished product. And so nowadays we're used to seeing, like the Quest 2 and the Valve Index and these products that are very much like a smooth user experience. Whereas not too long ago, it was very much a different experience from that. My first time trying VR was using a Google Cardboard. And I remember getting a Google Cardboard from my friend and spending hours and hours on the internet trying to figure out how I could stream, my Steam games from my Steam library onto the Google Cardboard so that I could play them, in VR. And it's one of those things where, like, while a lot of like the commercial side of VR is transitioning to this kind of smooth, polished kind of experience, that doesn't mean it has to limit the breadth and the depth that we can explore in VR and how much we can push the industry. And so one way to further VR is as one of these big players, with all of these resources and putting the highest budget possible toward pushing the the bounds of what is possible, right? And so a couple examples I have here are like really, really high-tech VR haptic gloves that use pressure so that you can feel the actual like texture of objects and things like that, or motorized VR treadmills that are extremely hard to move around and distribute to people, but as an experiment on locomotion, real natural locomotion in VR, it's a really, really amazing technology to play with. But so this is one way that you can further VR as these kind of parties. But on the other side, there are other ways that we can further VR, especially speaking about hardware, right from home. And so just a few examples I have here are like the Relativity VR headset, Slime VR, Finally Functional's VR shoes, and of course VR haptic gloves, which are the one that I'm, have touched the most so far. And so, these are definitely things that like, one of the ways that you can do this is just taking a technology that already exists outside of VR, and how can you kind of mix it with current aspects of the current XR community. And being able to do this stuff at home has a lot of really, really interesting advantages. Of course, there are cons like sometimes it's hard to source the right parts that you need. And so you have to make compromises in order to use parts that are available online or just like publicly. But there's also a lot of really interesting benefits. For example, if you're just doing, a DIY project, especially for hardware from home, it's okay to take risks. Safety is one thing, but as far as like, you're not a company that necessarily has to sell a minimum number of products, right? And so at that point, you don't have to be afraid to try something that's never been done before just because it might not necessarily sell. And so that leads to being able to do lots and lots of really unique things that you can't find anywhere else. Another thing is you can iterate very quickly. So without having to go through, extended, user testing, or having to, source parts that are custom that take a lot longer to create. You can use a lot of off-the-shelf things in order to increase the way that you can iterate and work on different projects and things like that very, very quickly. Along with working together with a community for your project can get you a lot of the information you need much faster. And of course, minimizing costs is a big part of this as well. And so if you're using off-the-shelf parts or if you're building things yourself, that lets you do things for a lot cheaper than if you say had to pay for a customer service and like a kitting company to manage, the distribution of a product. And so that lets you do things with a much smaller overhead, which ties back to the other ones as far as being able to take risk and being able to do it quickly. And all of these together lead to being able to fill in a lot of gaps that really, really big VR initiatives aren't able to do. So if there's something that doesn't necessarily look like it would affect, a huge percentage of VR users, that doesn't necessarily mean it's not something that's super valuable to still go after. And so a lot of these DIY projects can do things that can affect, a core niche community in a way that really, really big VR initiatives aren't able to do. So I'm going to talk about LucidVR, which is a project that I've been working on for the past couple of years to bring VR haptic gloves to the average user for much cheaper than what's currently available. So one of my biggest kind of issues with VR for a long time was the use of controllers and the way that is required to really, really interact with things in a lot of different VR experiences that are out there. I fell in love with VR over the pandemic when I was stuck at home during quarantine. And a lot of really amazing solutions for VR are out there as far as hand interaction. Hand tracking is one of them. But for a lot of the experiences that I really enjoy, like games, you want like a really reliable and also like a solution with feedback so that you can really like execute on a lot of these kind of actions. And so the current solution for that really is inspired by the past couple decades of non-VR consoles, which is just game controllers. And the main difference nowadays is they're tracked in 6DoF, right? But the big problems with that is now you have a clunky piece of plastic in your hand. And depending on the controller, if you open your hand to let go of something you're holding, it's going to fall out of the controller is going to fall out of your hand, right? And conversely, when you grab a virtual object, you're not going to feel the shape of that virtual object in your hand. You're just going to feel the shape of the controller in your hand. And so these are all things that I really wanted to see explored more. And they have been explored. VR haptic gloves are a thing. But especially VR haptic gloves with force feedback are extremely hard to get your hands on. They're made for companies. They're made in the enterprise sector. And so someone like me who was just like a high school student in quarantine couldn't afford any of that stuff. And so my only real solution was to just build them myself. And so that's what I did. And so this is the 5th prototype of what I call LucidGloves, which is a project to take VR haptic gloves and make them much more affordable and make them work in real VR games. This is my 5th prototype right here. And the way it works is it has various different sensors. So currently this prototype uses Hall effect sensors for actually measuring the position of your fingers, both the open and close and the side-to-side movement, as well as using just like remote control, like hobby servo motors for actually pulling your fingers back so you can feel the shape of objects. So it's about $60 in parts, so it's super duper cheap to build a pair. But it allows you to mess around with a lot of really fun interaction techniques that you wouldn't normally be able to do. And this is, this ties back to being able to iterate very quickly. This is the 5th prototype, but from the beginning, like it started out as something that was very much a minimum viable product. Like it was not durable, any of that. It was very, very rough. And this is just one of those kind of aspects of these DIY projects is that, yes, they do start out, very janky, but the general trend is an upward trend, especially when you're able to work with a, really, really powerful community to help you. And so I've been running a YouTube channel for this project called Lucas VR Tech that's gotten about 700,000 subscribers online between different platforms. And so it's led to an amazing community of makers that have really helped out with the project. So we have about 18,000 people on Discord who build their own gloves or based on the reference design, since this is totally open source. But because of the fact that it's open source, that also means they're able to take it and fork it and make their own crazy designs based off of it. So here's just a few really, really inspiring ones that I've been really, really excited about. But this has also helped to further the project because now you have one more source of information, but also faster and faster iteration because there's lots and lots of experiments happening in parallel, which is something that is really unique to having an open source project with a big community. And this doesn't necessarily have to just be limited to the gaming space either. So an article was actually recently published in Current Directions in Biomedical Engineering where some researchers took my fourth prototype, recreated it from the GitHub files, and then tried to use it to evaluate if it could be used for XR-based medical teaching. And what they found was it actually, in fact, was suitable for XR-based medical teaching. They just felt like the haptics could use some improvements, but that's hopefully something to be working on in the future. So I also want to talk about, like, because I've talked about like why it's really, really amazing and inspiring to see lots of DIY projects out there, but also I feel like a lot of these DIY projects are a very small percentage of the VR community, and also a very small percentage of the hardware community. And I think there are a few big key challenges that are in the way of that. So one of them is that it's really, really hard to actually make VR devices and custom hardware talk to each other, especially if you're new to this kind of thing. So there's a lot of really amazing communities out there with really amazing documentation on like how to make a VR game or app, for example, in a game engine, right? And there's also really amazing documentation on how to make custom hardware, even if that's like electronics or microcontrollers, that kind of thing. Like they're all really, really well documented, and so many people that love to help out with it. But how do you put those two things together and make them talk to each other? Because if you're not making your own VR headset and you're just making a peripheral, that's like an extremely big challenge, and it's not something that's super duper treaded ground. And so that's something that's really missing right now. Last semester, I actually helped to teach a class called Virtualizing the Human Body, where I taught a group of students how to make an Oculus Quest 2 talk to an ESP32 microcontroller, and then basically gave them free rein to build whatever they want. And we had some really, really amazing projects. There were VR treadmills, VR haptic devices, a VR skateboard, and like all of these kinds of things are just like being able to let your imagination run just once you're able to remove that limit. And that kind of process of connecting the VR device to the custom hardware is something we call the singularity. And it really, really leads to so many different possibilities. But even more than that, there's another further challenge, which is the phase of tech demos, right? And tech demos are amazing. They're a really, really great way to showcase the potential of hardware. But if you're looking for real impact from a piece of VR hardware, it's really, really difficult to do that if you have to go in and make every single experience yourself that you're trying to use that hardware for in a game engine, for example, or if you have to go and reach out to developers to actually get support in them. So for example, if we had to reach out to every single game developer to get support in the gloves, like that would be a really, really big challenge. And so one direction that's really helped with that is being able to just get native support as a VR controller. And so you're going to hear from Dan tomorrow about how we made a VR glove driver so that our VR gloves work as actual VR controllers. But it's something that really, really changes things, because now once you're able to act as registered hardware, it makes it much easier to interface with these apps, but there are still things that are missing, right? So like for us, like haptic support is really hard, being able to actually get the force feedback into different apps. And so that's something that we actually have to modify the different apps in order to do. But the call for action that I really wanted to go for here is just trying to brainstorm, like what are ways that we as a community could make it easier for people who are making their own VR hardware, or these budding like open source VR hardware projects. What are ways that we can make it easier to connect those to the software developers that are making the VR experiences that people are using? And right now, primarily that involves gaming, just because that's been the first really, really big source of VR entertainment. But I think that's also going to branch out to lots and lots of other areas as things move forward. Yeah, anyway, that's pretty much all I have budgeted for here. So if we have a little bit of extra time, I have a clip to show of reaction of the gloves. So this is Linus from Linus Tech Tips here. And this is the first time he used my prototype 4.1. And so you can see here's the finger tracking working. And here it is where he's actually testing the haptics. And so here when he picks up this card, he says it's thin because the game is actually rendering the difference between the size of, like, say, a can, for example, and the size of that card, which will be much thinner. Okay, so that's what I had for the presentation. So I'm ready to open it up for Q&A.
Thanks, Luca. Very interesting talk. So I'll take questions in the audience here and also on the channel. So if there's anyone with the first question in here for Lucas, I would. There's one. So hold on. At the very back, here in Minneapolis. So, hey, Nico.
Heyo. I'm just wondering where you're at with the with adding haptics to the display of the fingers.
Yeah, that's a great question. So kind of the biggest kind of focus for the gloves so far as like software support has been integrating haptics with the curl, just because that's the one that you notice first. So splay support is actually something that's coming into prototype 5 as far as the tracking. But so since splay is such a new thing, and not all games have support for splay, splay haptics isn't something that we've had a ton of like focus on yet. But of course, since this is an open source project, that is also one of those things where if a community piece of hardware comes out that does support it, that's one of those things that will push us to add that kind of support faster. So splay support, for example, actually in the driver is something that we started to prioritize support based on after some of the community hardware that came out started to support that kind of stuff. So if there was a similar situation with the haptics, that's when we would probably start messing with that.
Thanks. Anyone else? Yes. No worries. So a question from Bryan in the audience here.
Hey, Lucas, how's it going? It's Bryan from
Hello.
Northstar. And so my question for you is, what other open source hardware projects do you want to build outside of gloves? And do they involve an AR headset? And do you want to do that next week?
Next week? I would absolutely love to mess with Project Northstar. And if we could make it work with VR gloves, that would be super cool too.
Yeah. Another one from me, actually. So you shown some results from revision 5. Is there anything on the works? What's next?
So prototype 5 isn't fully finished. I still have to work on getting it polished enough to have it ready on the GitHub for people to start, flooding in and downloading it and starting printing and things like that. So my biggest focus right now is getting that one out. But I do also want to work on moving a lot of the hardware up the hand as well. So reducing the weight that is on the hand. That's probably going to be a big focus for prototype 6, as well as adding extra sensors for things such as like pressure, so you can feel like squishy objects versus hard objects, as well as messing around with temperature simulation. That's something that I've messed around with using like Peltier modules for, and that's one that I really want to mess with, like actually putting on the gloves soon.
Thanks. Another question here from the audience.
Hi, it's Nova from Stardust, though. So I was wondering, you're adding so many different new sensors and haptics to this glove. How do you ensure that that games even have like any compatibility to begin with? And also, when new sensors are added, like you're going to need some kind of standard to connect them, but it's iterating so fast. How do you manage that when OpenXR and such just don't have support really?
Yes, that is an excellent question. So one thing I forgot to mention back here is that the haptics, for example, those aren't something that goes through OpenVR or OpenXR in our pipeline into games yet. So currently, the way that we add the haptics in is the community is really like mobilized there as far as actually making the mods. So for example, the Boneworks mod, which is like my favorite mod for the gloves so far, wasn't written by me or Dan. It was actually written by one of the members of our just like community named Lars, who was just like really interested in, really likes the game and really wanted to make the gloves work in the game. And so that's something that we would be taking advantage of a lot as far as like every time we add something new, is we already have a lot of this hardware out, right? Like there are thousands of these gloves that exist just in the wild of people who have built them. And so they are the most valuable resource as far as bringing support for this kind of thing out there.
All right, looking to the audience, I think we're done. Last one, maybe? Okay, so we have time for a last question. There's a lot of interest.
Just a follow up to that one. I was wondering if you what do you see sort of in the near future? Modding is sort of like going to be the main thing, but do you see anything sort of a little bit farther down the line of I mean, have you, in terms of how developers have sort of reacted to it and that sort of thing, if there were something, I mean, let's say there was something like a Kickstarter or something like that, hypothetically, where there was a larger install base. I don't know. I'm just wondering what you think about that timescale.
Yeah, so we have talked to developers of a few different game studios. I'm not going to name specific names yet, but there is actually a real possibility of getting native compatibility in some of our favorite VR games that are out there. But as far as finding a general solution into adding it into more things, Dan actually has been working on something that will hopefully help with OpenXR, and I don't want to spoil his talk too much. That's something I'm also extremely excited about.
All right, so that's it for FOSS Day 1. Thank you so much, Luca, for this amazing work, and take care. Okay.
Take care.
Bye.